very much. Well, so I would like to thank the organizers for having me here. It's a nice place. And yeah, so in my first lectures, I'll talk about non-invertible symmetries. And the main reference I'll give is the TASI lecture notes I wrote this summer. You can find most of the references there. I will, since this is a Blackboard lecture, I will probably not give any specific reference throughout. So you can look at the TASI lecture notes to see what are the documents. I also find this lecture uniquely challenging in terms of the diverse audience we have here. Because we have mathematicians here, we have high-energy physicists, we also have some condensed matter physicists. I really don't know how to prepare the lecture for such a place. And I have to confess that I'm a physicist. So my approach, my presentation will be intrinsically physical. In fact, when I wrote my TASI lecture this summer, I kind of purposely steered away from the more categorical formalism of generalized global symmetry. Try to give more physical examples. And that will probably be the same route that I will follow throughout the lectures here. But you know, if you have any questions, just please stop me anytime, and I'll try to give an alternative perspective. I might not always succeed, but I'll try my very best. All right. So let me say a little bit about the plan of the lectures. So in the first 1 or 2 lectures, I will spend quite a lot of time talking about the simplest non-trivial example of the non-invertible symmetry. And that already exists in arguably the simplest many-body system or simplest quantum field theory of all, which is the Ising model. You might be surprised that it's already 2023, but somehow we are still learning new things about Ising model. And then I will talk about some higher form symmetries. And condensation defect. So to be clear, by Ising model, I mean Ising model in 1+1 dimensions or 2 space-time dimensions. But once we go to higher than 2 space-time dimensions, the non-invertible symmetries have a highly non-trivial interplay with what is known as the higher form symmetries. And the simplest example of non-invertible symmetries in diverse dimensions will be is actually known as the condensation defect. I'll spend some time talking about it. I should say that higher form symmetry by itself should be another set of lectures, but I won't have time to cover it in any detail. So I'll try to be brief about higher form symmetries. If you guys already have the background, that's excellent. If you don't, I encourage you to look at I think it's section 1 of my TASI lecture note, where I have some lightning reviews. And I'll also be happy to talk about it more during the coffee hours. And then I'll talk about a very important technique or construction in getting non-invertible symmetry in general dimension. And that's known as half gauging. And finally, in the last lectures, I'll try to make some contact with the real physical system. In particular, we will address why do pions decay. And as I said, I think one particular challenge about me giving this lecture is that to this diverse audience, I guess only half of the people know what pions are. But hopefully you will still find it interesting. So for Ising model, it's really the simplest quantum field theory or lattice model of all. So I think it's really worthwhile to spend a lot of time understanding how this new kind of symmetry arises in that particular case. So in my TASI lecture, you will find I presented 6 different constructions for the non-invertible symmetry in the Ising model. So I won't have time to give you all 6 during my 5 lectures. I can do that, but then I can spend all my 5 lectures on Ising model. But let me tell you what are they. So the first one, which is the one I will talk about, is to construct it from the transverse field Ising model. So this is a Hamiltonian lattice model. So this will be the focus of my first lecture. The second one is closely related to the first one. It's known as the anionic chain. It's also a lattice model, and it's in the Hamiltonian language. The third one is also closely related. I should say that all 6 constructions are somewhat related, but the presentations are different. The third one is known as the Asen-Fendley-Mohn lattice model. And this one is a Euclidean lattice model. So these 3 constructions are on the lattice. There are also 3 different ways to think about the non-invertible symmetries from the continuum. The first one is from bosonization, which depending on how much time we have, I may or may not mention it. So bosonization from Majorana CFT. The fifth one is to think about topological lines in Ising CFT. You might say that this one is probably the most categorical one. I will not talk about this perspective. I'll be happy to talk about it during the break. And then the sixth one is number 3 here. Which in retrospect, one can say is the most powerful construction of all. All right, so I will focus on this one. I probably say a little bit about this one, and of course I'll talk about the last one. All right. That's the plan of the 5 lectures. Any question at this point? Probably not. Actually, before we go into the detail, how many of you have learned Ising model? You raise your hand if you have. Okay, that's great. Great. How many of you, when you first learned Ising model, you learn it from the statistical Ising model point of view? Okay. How many of you learn it from the transverse field Ising model point of view? No, great. What about the continuum Ising CFT? Okay, some of you guys, great. Okay, so this one will be more closely related to the statistical way of thinking about the Ising model. But the presentation I'll give will be based on the Hamiltonian one. The two are closely related. You just have to do the transfer matrix from one to another. Anyway, I'll start from the basics so that hopefully everyone can follow. So before we talk about Ising model, let me say a little bit, give some overall general introduction to what this topic is about. What is a non-invertible symmetry? Many of my friends, and especially mathematician friends, find the term extremely offensive. Symmetries are supposed to be proved. What do you mean by non-invertible symmetries? In fact, I myself have been on the fence on this question, on both sides of the fence for years. I think in the beginning, I don't think about them as symmetries. I call them non-symmetry. But at that time, no one was working on it. But then, the more I studied it, the more I found they are closer to the ordinary symmetries that we know of. And hopefully, one of the goals of this set of lectures is to convince you why that is the case.
So sorry to heckle, but the reason we find the term offensive is because it's not a new thing at all. You first into it when you linearize. If you start with a group of symmetries and you linearize, the span will contain non-invertible symmetries. So it is a fake distinction. Once you're in a quantum world, meaning a linear world. It's a classical world that makes sense.
I think every single person has their own unique reason.
This is universally shared.
That's what makes it even more offensive. People find it offensive in different ways. I really agree with you, Constantine. In fact, that's one of the things I address in section 1 of my TASI lectures. And the question is whether or not you are allowed to take this span. But great, yeah, I think Constantine agreed with me that it is offensive. I think that would be one motivation that you guys might find this lecture interesting. I wasn't going to address Constantine's question in this lecture, although I did in my TASI lecture in June. But now that Constantine raised the question, I might as well. Let me start with that. Let's start with something very standard. Let's start with Wigner's theory. I'm not going to prove it, but I'm just going to state it. So Wigner's theorem states that in quantum mechanics, it's absolutely crucial that we're talking about quantum mechanics here, not quantum field theory in general dimension. Some of you might say that, oh, but you take any quantum field theory, any many-body system, you take the space to be very small, you put it on a torus, you put it on a sphere, make the size of the system very small, then it's effectively a quantum mechanical problem. That is correct. But by doing that reduction, you are losing information. You forget about the beautiful fact that this underlying quantum mechanical model comes from a higher dimensional system. So let's do that. Let's think about it that way for the time being. Let's say you are looking at a quantum mechanical problem. Then Wigner said, every symmetry is implemented by a unitary or anti-unitary operator. Well, it's anti-unitary when it's a time reversal symmetry, but otherwise it should be unitary.
Sorry. What is the difference between quantum mechanics and quantum field theory?
Great, yeah. I think that's the thing I would like to address. Actually, I wasn't planning to, but maybe I should.
Because this theorem is stated in Weinberg's book.
Yes.
For quantum field theories.
Well, Weinberg didn't know about non-invertible symmetry. I mean, of course, there's ambiguity on what you consider to be a symmetry. And in Wigner's formulation of his theorem, symmetry is defined to be something that preserves the norm. But hopefully I'll try to justify why that is not necessary when we go to the
Sorry, so the theorem is that every endomorphism that preserves the norm is unitary?
Well, I think when it comes to the precise mathematical statement of a theorem, I'm basically illiterate. So I'll probably plead the fifth on that. Any other questions? I might not be able to give an answer. Now, one important thing about unitary operator is that its inverse is given by its dagger. So every unitary operator has an inverse, and is in particular invertible. Now, coming to the earlier question, what's the difference between quantum mechanics and quantum field theory? When you go to quantum field theory, or the lattice quantum, in general dimensions, one important difference compared to quantum mechanics is that you have a notion of spatial locality. And that gives you additional constraints on what you might call a symmetry. And spatial locality gives you more constraints on the one hand, and also give you more possibilities for what symmetries can be. And that leads to two generalizations of the ordinary symmetry. The first one is that symmetries can act on extended objects, such as Wilson lines, or some surface, a worksheet of a string, etc. And this gives the generalization known as the higher order symmetries. We'll only briefly talk about in later lectures. And the second generalization is that symmetries can be non-invertible. But this can be non-invertible. But this sentence has to be clarified appropriately. But the second statement has to be it requires some qualification because, as Constantine already said, you take an ordinary set of unitary operators that generate the ordinary global symmetry in your quantum mechanical model. You can take the span of that symmetries, of those symmetries. And obviously, by taking some linear combination of those symmetries, you will have some non-invertible element. Let's do some very stupid example. Let's say you are studying the hydrogen atom. That's a quantum mechanical problem. So that there's a Z2 symmetry. It could be simple harmonic oscillator or whatever. Any quantum mechanical model with a Z2 global symmetry. And what does that mean? That means you have a unitary operator U such that U squared is 1. But once you consider the span, consider the projection operator. 1 plus U over 2. Projection operator commutes with the Hamiltonian. So we have U commutes with the Hamiltonian. projection operator also commutes with the Hamiltonian. And in quantum mechanics, you would say a minimum requirement, I'm not saying that it's all the requirement, but a minimum requirement for symmetry is that it's an operator that commutes with the Hamiltonian. Well, projection operator is an operator that commutes with the Hamiltonian, but it obviously does not have an inverse. The projection operator has a huge kernel, which are all the Z2R states. But you don't tell your friends that you discover a non-invertible symmetry when you first learn about the projection operator. And the underlying reason is because you know the projection operator is something made out of the original unitary Z2R. It's not something new. It's very much a derivative object from something that's invertible. Now, there's one distinction between quantum mechanics and quantum field theory. When we go to quantum field theory, there will be a preferred basis for the symmetry operators. And there will be examples of symmetries where you cannot decompose it into invertible constituent. In that sense, you have some genuine non-invertible symmetries in higher dimension. But in quantum mechanics, you never have them. In quantum mechanics, when you consider the span of all the unitary operators that commute with the Hamiltonian, it's just an algebra. I mean, algebra has a lot of non-invertible elements, but who cares? And that's one very important distinction between quantum field theory and quantum mechanics. And I'll try to come back to this point repeatedly throughout the lectures. But the takeaway message is that there's no interesting non-invertible symmetry in quantum mechanics. Maybe let me say something about this. So before we go to non-invertible symmetry, let's do an ordinary symmetry. And I would like to illustrate some of the points I just made. Let's consider ordinary U1 global symmetries. In these space-time. So in a relativistic quantum field theory, one definition of having a U1 global symmetry is the existence of a local operator, or maybe what some people would call a point operator, J mu of x. So here, x collectively denotes the space-time coordinates in these space-time dimensions, and this mu index runs from 0, 1, all the way to d minus 1, such that this operator obeys the conservation equation. So I will view it as a 1 form. Some people like to view it as a d minus 1 form, which I admit is better. Let me do it in the conventional. Now, what we learn in quantum field theory textbooks is that given such a local operator satisfying the conservation equation, you can define an operator. Is blue visible to the people in the back? Okay. You can define a conserved operator to be u theta over, to be u theta as exponential integrate over the whole space at a given time. So you take the time component of the current, you integrate it over the whole d minus 1 dimensional space. that gives you the charge. And then you further take the exponentiation of it, that gives you a unitary operator. That's why this operator is called U. And it's doing a rotation by angle theta. So this is a unitary operator, and it's conserved. It's conserved because if you hit a time derivative, the time derivative can be brought into the integrand, assuming some smooth fall-off boundary condition. And d0, j0 can be substituted to be a total derivative in space. Here we are doing a total integral over the entire space. And it's just assuming nice boundary condition. And that's what you don't normally consider to be a symmetry, right? Some conserved operator that's invariant under time evolution. That's what I meant by conserved. Mechanically, that means U theta as an operator commutes with the Hamiltonian. So far, everything works just as in quantum mechanics. This is an operator acting on the Hilbert space. But in quantum field theory, there's something more creative you can do. And that is known as a topological defect. What is a topological defect? If you are a relativistic quantum field theorist, when you see this formula, you should find it offensive because it picks up the time direction out of the d space-time directions. And Einstein taught us that time is really on the same footing as any other directions, especially if you are in Euclidean signature. So a more covariant expression for U theta will be to define it on a general d minus 1 dimensional manifolds in your space-time. And for simplicity, let's take it to be a closed manifold. And here, for simplicity, I can also take my space to be some compact closed space. And then take the integral. So J here, I take it to be a 1 form. So if I take the Hodge dual, that becomes the d minus 1 form. And I can integrate it on my d minus 1 manifold. But now the conservation equation should be upgraded to something more general. Conservation originally means that here's the time direction, and you have your operator here. You compare this operator with that operator, you get the same answer. But now that we are doing things more covariantly, we can integrate our operator on some general d minus 1 dimensional manifold. And by Stokes theorem, because star J is a closed form, that means Euclidean correlation function involving U theta of n equals U theta of n prime, where n and n prime can be smoothly deformed to each other. Now, here I would like to make an important distinction in the terminology. By operator, I mean the operator acting on the Hilbert space. It's something that supported at a fixed time, and in this particular case, it has supports over the whole space. For higher form symmetry, you will only have support in part of the space. But for ordinary symmetry, it's an operator at a given time that has supports over the entire space. Defect is something different. Defect is something that's localized somewhere in space, but extends in the time direction. So let me draw it in pictures in 1 plus 1 dimensions. I'm not doing very well in my blackboard. So let's say my space-time is a cylinder. This is time. I might compact it by my Euclidean time direction at the end of the day. That's not going to matter too much. And this is my space. So an operator has support here in the blue locus. And you should really view it as an operator acting on the Hilbert space H. U theta. Okay, let me just on the other hand, a defect. Here, this is e to the I theta integral of J0 dx. So here I'm taking the particular special case of 1 plus 1d. D is 2. So it's just taking the time component and integrating it along space. But for the defect, we're integrating along the time direction of Jx. And it runs in this direction. Now this object is not an operator. It doesn't act on the Hilbert space. In fact, it gives you a different Hilbert space. You're doing your quantization on this circle. For instance, maybe you're dealing with a free complex scalar field. And here you are doing a periodic boundary condition. By inserting a defect, it means that your complex scalar field is no longer periodic as it goes along the spatial circle. It gets rotated by a phase theta when it goes around the circle. It could be an anti-periodic boundary condition with theta is pi. So such a defect is not an operator acting on the Hilbert space. Rather, it gives you a twisted Hilbert space, which I denote by H with a subscript theta labeling the group element. In this particular case, an angle of a U1 global symmetry. And this is something that you really don't have in quantum mechanics. And that distinguishes symmetries in quantum mechanics versus quantum field theory. In quantum mechanics, you only have the first one. You have an operator. In quantum mechanics, you don't have the notion of space. And there's no sense to create a defect in quantum mechanics. In quantum field theory, you do have a notion in space. And you can create something localizing space that persists in all time. So the takeaway message from this discussion is that symmetry in quantum field theory, a lattice model of higher dimensions, it serves two purposes in life. A, it should serve as a conserved operator acting on the Hilbert space. B, it should serve as a defect that modifies the quantization and give you a new Hilbert space, which is sometimes referred to as the defect Hilbert space or the twisted Hilbert space. And the consistency of these two complementary pictures of every global symmetry give you enormous constraints on what symmetry could be and what are the possibility of global symmetries in general dimensions. And I should say that that is one of the ways we constrain the possible generalized global symmetries, say in the Ising CFT, from this particular perspective. Probably won't have time to talk about that. And let me make a few more comments. If you are a quantum mechanical person, so coming back to your question, you can take an operator, you can multiply it by 1/7. You can multiply it by any complex number. You can take any complex linear combinations of your conserved operators, and that gives you another conserved operators. It still acts on the Hilbert space. And that is the case in quantum mechanics. But that is not so when you are in quantum field theory and you want to, you also demand the linear combination to have a meaning in terms of a topological defect. So as an operator, of course you can talk about this quantity. It still acts on the Hilbert space. But as a defect, you don't know how to think about it. And the reason is because for every symmetry, the slogan is that it should give you A, a conserved operator, B, a twisted Hilbert space. But there's no way for you to divide a Hilbert space by a factor of 7. Therefore, if U theta is a good topological defect, no one tells you, no one guarantees you that 1/7 times U theta is a good topological defect. But that gives you a notion of integrality among the space of global symmetries. And that's really the essence of the whole discussion of generalized global symmetries. You cannot really divide, you cannot take general complex linear combinations of global solutions. Any question at this point? It's a little bit abstract. Yeah.
If I were to make up some, say, line in my theory that in part lies inside my time slice and in part extends in the time direction.
Right.
How do I think of that? Does it both modify the Hilbert space and act on it?
The short answer is yes. So let me give you a quick example. So the question is, what if my line wraps in a more general cycle, say in my space-time, or takes a more general shape in my space-time? What's the interpretation of that? So for instance, this can be your space-time, and you can have a line that goes like this, for instance. So it wraps both the time direction and the spatial direction. And this should be viewed as an operator acting on the twisted Hilbert space. So this gives you some u prime that acts on a twisted Hilbert space and gives you back a twisted Hilbert space. In 1+1 dimension, you can make this even more general. I think in mathematics, this is related to the tube algebra of the diffusion category. So let me now elaborate more on this. You can even have some map from one twisted Hilbert space to another twisted Hilbert space, but I'm not considering that more general possibility. You can even have some junction between them, etc. Any other questions? Okay. All right. So this operating effect principle is most easily stated in continuum relativistic quantum field theory. Basically because if you look at these two pictures, they're related just by tilting your head by 90 degrees. On the lattice model, the relation is more obscure. Of course, if you're working a statistical Ising model, for instance, then the relation is clear because in a statistical model, the time is on the same footing as the space. But if you work with a Hamiltonian lattice model, it's less clear. And I would say that's still an open question in the field. All right, so that's a little bit abstract. I probably won't have time to talk about the detailed example, the application of this operator defect principle in the case of Ising CFT, but I'll be happy to talk about it at a break. If there's no further question, let me go to the transverse field Ising model. I'll say a little bit about this perspective along the way. And this will serve as our first encounter of a non-trivial non-invertible symmetries. Okay. So what is the transverse field Ising model? I'm going to say in the next 5 minutes, you can find it on Wikipedia. I mean, there's a Wikipedia page called Transverse Field Ising Model. So completely standard. So let's say I'm going to work at a closed channel. So this is my space. It's a 1+1D model. Let me say that. So my space is one-dimensional. It's a lattice model, so my space is discretized. By the way, the reason I started with the transverse field Ising model is because everything I'm about to say is just about matrices. There's no mystery at all. I mean, some of you might be more familiar with lattice models, some of you might be more familiar with category theory, some of you might be more familiar with quantum field theory, but I hope everyone is familiar with matrices. That's why I find this example extremely concrete. You can literally put it on Mathematica in real time. Okay. So my space is some discretized points, the sites, if you wish. I'm going to label the site by this index j. J equals to 1, j equals to 2, all the way to j equals to capital N. And as indicated by the way I drew it, it's a periodic chain. Okay? So j, the index, is identified with j plus 1. It's a closed period. Now, at every site, I have a qubit. At every site, I have a qubit. Now, what is a qubit? That means my Hilbert space at every site J is a C. Now, on every qubit, I have two, I can consider operators acting on them. And they can be generated by the poly X matrix and the poly Z matrix. So instead of writing them as sigma X and sigma J, I'm just going to write them as Xj and Zj. So for instance, locally, this is 0, 1, 1, 0. And importantly, the anti-group. And your total Hilbert space is a tensor product of the local one. All right, so far so good. So the dimension of my total Hilbert space is just 2 to the n. The fine-dimensional system is literally, you can literally write every matrix, every operator as a fine-dimensional matrix.
I'm sorry, do we want to include the other operator?
The what? The y operator?
Other poly operator?
So I wrote down z and x. There's one left over, that's y.
Yeah.
Yeah, so I can include them, but it's expressible in terms of z and x. My Hamiltonian for the original problem is completely written in terms of z and x. Well, of course, you should have the y in mind. I'm just too lazy. So I should have first written on this side, right, and then lift it up, and then write on this side. Okay, I'll learn that lesson. Okay. All right, so that's the Hilbert space. That's the set of operators, x, z, and also y, and also any general linear combination of them. We're not talking about symmetry yet. I haven't even told you the Hamiltonian yet. So I'm allowed to take arbitrary linear combination of my operators. So what's my Hamiltonian? This is a 1 plus 1D Hamiltonian lattice model. So I have a Hilbert space, and then I'm about to write down the Hamiltonian. My curly H will stand for the Hilbert space. My normal font H will stand for the Hamiltonian. So the Hamiltonian takes the following form. You take the sum from j equals to 1 to n, Vj minus a coupling constant g is the nearest neighbor interaction of certain. Sometimes it's more conventional to swap the z and x, but it doesn't matter that much. All right, so that's pretty much it. This is a Hamiltonian, this is a matrix, you can put it on a Mathematica, you can solve the eigenstate, solve the spectrum. In fact, the model is exactly solvable. We don't even need Mathematica to do it. The question we would like to ask is, what are the global symmetries of this simplest many-body system? Now, as many of you know very well, Ising model famously has a Z2 symmetry. That's almost a defined property of the Ising model. It has a Z2 global symmetry. And I'm going to write a unitary operator that implements the Z2 as eta for no good reason. And it's the product of j equals to 1 to n. Let's take a moment to look at this equation. So this is some operator acting on my Hilbert space. You can check that eta h is h eta. The first term is made out of z's, so it obviously commutes with eta. The second term is the nearest neighbor interaction between the two sides. Each individual x anti-commutes with eta, but since everything is quadratic in x, the whole thing commutes with eta. So it's super clear that we have this Z2 global symmetry at every value of G. Each term is separately Z2 even. So that's one symmetry of the model. Now you should think about this expression as the lattice version of this expression. So I'm taking a product of operator at every local site. So this operator spans over my entire space. But it's an operator, so it acts at a given time. So it corresponds to this picture. Now you might ask, what about the picture down here in terms of a defect? How do you represent that on the lattice? So this is the operator. Let me use a different color. Where's my color?
Plenty of colors here.
But I should have one
Here. This one.
So this is the operator. Now a defect is something different, as we emphasized. The defect gives you a different computation. And a defect gives you a different Hilbert space. Sorry, I misspoke. A different Hamiltonian. So a defect changes the Hamiltonian at one site. So most of the terms in the Hamiltonian look identical to the one above, except for one term at the link between the nth site and the first site. You flip the sign at one link. So this object modifies the Hamiltonian at one link. So it's localizing space. But it's not an operator. This modification persists in all time, and that's why it's a defect. So you can see that in the continuum, these two pictures look very closely related. They're just related by a 90-degree rotation. But on the lattice, they are represented by something completely different. Of course, they're also related on the lattice, because you can think about this modification as applying a Z2 operator on one side of the link. One of them is an operator acting on the original Hilbert space and commutes with the original Hamiltonian. The other is a modification of the Hamiltonian at one state. All right, so far everything I said is completely standard. Let's ask the following question. At a generic value of G, that's the only global symmetry you have. But at G equals to 1, which is a special point, for those of you who have studied the Ising model, you might know that at G equals to 1, this model flows to a gapless CFD. This is the critical point. So at the G equals to 1 critical point, is there an additional symmetry operator that commutes with the Hamiltonian and act H. Well, let's take a look. So at g equals to 1, the coefficients for these two terms become identical. So if you look at the Hamiltonian, you might ask yourself, maybe there's a symmetry that exchanges zj with xj plus 1. After all, the first time we learned symmetries, how do we define it? Someone hands you a Lagrangian, someone hands you a Hamiltonian. And sometimes people just loosely say that a symmetry is some transformation of the fields that leaves the Lagrangian or the Hamiltonian invariant. Right? That's usually how we first learn symmetries in the textbook. You have some scalar field, you do some transformation, it leaves the Lagrangian invariant, and that's good enough as symmetry. In this case, that does appear as a symmetry, because if you look at the Hamiltonian, you exchange dj with xj plus 1, that leaves the Hamiltonian invariant. So why isn't that the answer? Now, a very senior collaborator of mine told me repeatedly that in theoretical physics, you should never write arrows in equations, because you will only confuse yourself by doing so. You should always write equality. That might not apply to every case, but it's actually it actually completely captures the issue in this particular case. Let me demonstrate that. By writing an arrow, you might think, oh, this looks like a Z2 symmetry, right? You swap Zj with xj plus 1, you swap it back. Now, let's think about it a little bit more. Let me ask the following question. So this is a question. Does there exist a unitary operator? After all, if it were really a symmetry, Wigner would insist that it is implemented by a unitary operator. So let's ask, is there a unitary operator U that implements this transformation? Well, you can easily falsify this statement. So let's do it in real time. Let's suppose there were such a unitary operator. Then U acting on the product of Zj, which is just doing a unitary transformation on the Z2 operator. This is the definition of eta, as you can see over there. Now I can use the equality over there to write it as this. But then you are taking, see, all the terms pair annihilate. Is that clear? You have x1, x2, the next term is x2, x3, the next term is x3, x4. So every single one of the xj's appears twice. Now maybe I should emphasize that these are Pauli matrices, so zj squared equals xj squared equals 1. So this is nothing but 1. So what we are saying is that if there were such a unitary operator, then eta has to act as plus 1. But that's a contradiction, because eta is a Z2 operator acting on this 2 to the n dimensional Hilbert space. It acts as plus 1 on half of the Hilbert space. It acts as minus 1 on the other half. It's not the identity operator. So this immediately tells you that there cannot be such a unitary operator. And that should make you confused, because you see with naked eyes that this Hamiltonian has this kind of symmetry, which, let me put in quotation marks. But you cannot find such a unitary operator that does the job. And this will be our first encounter of the non-invertible symmetry. Any question at this point? this is really just a statement about matrices. The claim is that you cannot find a unitary matrix that does this transformation, which appears to be a symmetry of the Hamiltonian. So do we have a symmetry or not? Well, let me write down an operator that does the job. But you will see that there's a price to be paid.
So this argument really works for closed systems.
That's right. That's right. For closed, first, if it's an open system, we wouldn't even dare thinking about such a symmetry, right? Because you shift the lattice by half a size, so you wouldn't have this symmetry. So it doesn't work for a finite open system. And we just show that there isn't such a symmetry for a closed system. You might say, what about infinite chain? Well, infinite chain is something in a way much more subtle because you are hiding the boundary condition at infinity. There is a way to make it precise, say by studying the rigorous von Neumann algebra acting on the infinite chain, but let me not go down that path. The spirit of the whole lectures will be that we always work in compact spacetime. Sometimes we work on spacetime with boundary conditions, but we try to avoid infinite spacetime. Any other questions? And I should emphasize that when we define symmetries in continuum quantum field theory, one universal way to define it is also to put it on a compact space and classify the conserved operators, such as this is what we usually do, say in Ising CFD. Any other question? Okay. Oh, yeah.
I have a very naive question. So in the definition of H eta downstairs, it seems like you made an arbitrary choice of flipping the sign at position n.
Right.
But somehow the Hn, the notation suggests that this does not depend on the choice of n.
It's an excellent question. So the question is, here I made a choice of one particular link to flip the sign. Does that matter? And the second part of the question is about notation, because I didn't write the position of the link on the left-hand side of the equality. So let me first answer the second part of the question. To be more precise, we better put a dependence of the location of the twist. But there's still in some sense that you don't have to. And in the following sense, you can compare the twist at link n,1 versus a twist at link 1,2. And you can show that they're related by unitary transformation. You can write down an explicit unitary operator. In this case, it's actually very simple. That when you conjugate H eta with a twist at the n,1 link, it gives you the Hamiltonian with a twist at 1,2. And that is the statement, when you go to the thermodynamic limit to the continuum, that is the statement that this line is topological. It's not true if you just do an arbitrary twist. If the system doesn't have such a Z2 symmetry, and you do a twist somewhere in your Hamiltonian, it's generally not going to be the case that you can move it by a unitary operator. That's an excellent question. Any other question?
I have a related question. So what is the practical procedure when I start with a Hamiltonian and an operator to compute this? I would imagine that I would somehow have to change the periodic boundary conditions with acting with eta. I don't really see how this happens.
Right. For invertible symmetry, the practical way to proceed is that you first pretend, so you work locally. You look at one link, and you just apply a unitary transformation on one side of the link. So what do? I look at this Hamiltonian, I pick the n,1 link, and I apply my eta transformation. I conjugate every term by eta to the right of that link. So I'm doing the conjugation on x1, on x2, on x3, but not on xn, not on xn minus 1. So you see that when you are far to the right, if you are looking at x17, x18, you don't flip the sign, because both of them got flipped. If you look at far on the left, if you look at xn minus 2, xn minus 3, that terms also remain the same. The only term that got flipped is at the junction. So that's the general rule to write down the twisted Hamiltonian when you have an invertible symmetry. For non-invertible ones, it's much more subtle, and I probably won't talk about it.
So you're saying that to create a defect, it creates like the symmetry string, but it ends at the point where the defect
Can you
is.
say again? I didn't quite follow.
Yeah, so I was saying you're saying that to create that defect,
Yes.
you end the string at the string though, like the symmetry.
Yeah. You
Right?
can
That was
think
the
about it
entire
that
line
way.
where you end it.
Yeah, you can think about it that way. I guess this is the end of the first lecture. Any other question before we close? All right. If not, I'll continue the discussion after the break. Thank you. All right, let's continue. So we were asking, what would be the operator that does the job? I wrote something just 1 minute ago, but I think it was too small and too complicated. So let me not start with that. Okay, so before I tell you the explicit expression of that operator, let me tell you what it does. So I claim there's an operator which I denote as D that does the following. So first of all, it commutes with the Hamiltonian only at G equals to 1. So it satisfies the minimum requirement as being a symmetry. It also satisfies many other nice things. It commutes with the Z2 operators. In fact, when you multiply the Z2 operator, it equals itself. That's already included here. Naively, you might think, oh, maybe I have a Z2 cross Z2 symmetry, the Klein group. In that case, when I multiply the first Z2 with what might have been the second Z2, I should get something else. But you don't. You get back the operator D itself. Now, there's one more thing I want to say, which is on the original Ising model, there's a lattice translation symmetry. So let me write it as T Ising. Again, this is just a matrix that you can write down very, very explicitly. Let me not do it in real time. I could do it if someone really wants me to do it, but unless otherwise request, let me just formally denote it as an operator T Ising. And what it does is to basically takes J to J plus 1. Yeah. Even though I just said we should never write arrow, but here I'm just being lazy. In this case, there's no subtlety. It's really an honest to God translation operator that maps every xj to xj plus 1, zj to zj plus 1. No funny faces, it just does the job. And this operator, because we are on a periodic chain with n sides, T Ising raised to the nth power is 1. So on the lattice, you can think about it as a Zn symmetry. Okay, n is the number of Ising sites. It's not an internal symmetry from the lattice point of view. It moves the lattice, it moves the site around. Well, so one very obvious statement is that eta commutes with the lattice translation, right? Because it's the product of the z's across the entire lattice. Okay. Now, this operator T, it also obeys that nice property. dt Ising is T Ising D. So far so good. It looks like a nice symmetry operator. But the weird part is the following, that this operator does not have an inverse. That's the bad news. It commutes with the Hamiltonian, it's translationally invariant, it satisfies somewhat exotic algebra with eta. It does not have an inverse. It's not a unitary operator in particular. But it does the right thing that we want. What is the right thing that we want? We want to exchange zj with xx. And you base this property. Yeah, that's the one. But notice that this equation is written in a different way than this wrong equation. So I'm going to, throughout my 5 lectures, I'm going to try my very best to put all the wrong or gauge non-invariant expressions in quotation marks. They're only supposed to be inspirational, but they are not strictly correct. So you want something like this. But the best you can achieve is this. What's the difference? The difference is that we move the operator that does the job to the other side of the equality. It seems like a completely innocent move. And we write both equations all the time when we talk about ordinary symmetries in quantum mechanics. We write U and H commutator equals 0, or we write U inverse equals H. And for unitary symmetries, they're equivalent. There's no big deal in writing it one way or another. But when we talk about non-invertible symmetry, only one of the 2 equations makes sense, because you don't have an inverse. And that's what's going on here. This equation makes sense, but there isn't another version. There isn't the alternative version up there. In fact, if you assume there is that version, you immediately run into the contradiction we just arrived. Okay? So I'm just claiming that there is such an operator D that satisfies this property. Is it a Z2 or not? Well, it's not, because it doesn't have an inverse. So what happens when you multiply D with D? What you found is that you get a projection operator. Eta is the Z2 symmetry, so this is the projection operator, times the lattice translation symmetry.
Sorry, does this follow from what you've written before, or this is just another fact?
I don't think it necessarily follows from what I wrote before. I'm not exactly sure, but these are all true facts.
I mean, D could have just been 0 with what we just wrote before, no?
What?
D could have just been 0 with only the facts you wrote before.
That is true, yeah. But that would not be compatible with okay. Now, for those of you who have studied non-invertible symmetry, this equation must look somewhat reminiscent, but not exactly the same. First, there's a factor of 2. Now, take my words, don't worry about the factor of 2 so much. It's actually very important, but don't worry about it too much. At this stage, you could have gotten rid of the factor of 2. You can say that, I'm just going to redefine my D by √2 and then get rid of it. At this point, no one tells me the normalization of D. That's not the whole story, but let's take that perspective. Let's not focus on the 2. The real difference between this algebra and the one that you might have seen in the continuum is this factor of the lattice translation. This factor becomes almost 1 as you take the thermodynamic limit. Right? Lattice translation by one side will become nothing as you take n to be very, very large and focus on the low-lying state. So this algebra will smoothly connect to the one in the continuum. So I'll use it, write a different letter, E. This is the non-invertible symmetry in the Ising CFT, whereas this is the one on the lattice. And on the lattice, you see this intrinsic mix with the lattice translation symmetry. In the continuum, this is a symmetry that's completely internal. It doesn't mix with the space-time symmetry. On the lattice, there is some mixing with the lattice translation. It's telling us something very interesting. I'm not going to say too much about it, but let me just point out this fact.
Is that a characteristic of the
of non-invertible symmetries on the lattice?
It's not true for all non-invertible symmetries on the lattice, but it is the case for this particular one.
Okay.
In fact, on the lattice, there is a way to get rid of the lattice translation. And that's one of the 6 constructions I listed in the last lecture. But as far as I know, if you want to insist on a tensor product Hilbert space, then you have to live with that mixing with the lattice translation. It's some tension between the fact that you have a tensor product Hilbert space and an internal non-invertible symmetry. It's some kind of anomaly. Okay. Sorry, say again?
You switched the 2 boards on the left.
Okay. All right. So just to prove that I'm not lying to you, let me write down the explicit expression for that operator. And in the rest of the lectures, I'm going to tell you how to derive this operator. And I think this is arguably the simplest non-invertible symmetry. Because you can literally write it down as I'm going to do it now. There's a face. Don't worry about it too much. It's there to make the formula a little bit nicer. Okay. So this, I claim, is the operator that does the job. It's very complicated, right? It's a mouthful. You might be wondering why I remember the explicit expression without looking at my notes. But don't worry about it. The details don't matter. Later, I'm going to give you a more conceptual viewpoint on this. But let me point out some facts. So first, it's very explicit, okay? Everything is just made in terms of matrices. Right? And you can literally do it, put it on Mathematica in real time if you're not paying attention to the lecture. It's really simple. And once you put it in Mathematica, you can check every equality there in just one cell. Now, this part of the operator is unitary. This is actually a unitary gate. This little piece is unitary. Very easy to check. I'm not going to, but maybe it's an accident. Similarly, this operator is also unitary. So this part is just a product of local unitary operators. So let me call it UKW. Some people might already know what KW stands for, but let me not spell it out. The part that makes it non-unitary is this part. This is the Z2 projection. So it's almost like an invertible symmetry, but not quite so. But now let's recall the projection operator example we talked about at the beginning of the last lecture. Projection operator is something I took to be the stupid non-invertible symmetry in quantum mechanics. Now, is this guy stupid? Let's try to think about it. I claim this guy is not stupid, because if you just take UKW, this is unitary, but it does not commute with the Hamiltonian. This is something you can explicitly check. So by itself, it's not a good symmetry. And you really have to multiply it by a Z2 projection so that the whole thing commutes with the Hamiltonian. In fact, this UKW is not even translationally invariant. That's obvious because I pick one to start. And I go all the way to here. And I even did something slightly different at the very last site. You see that I don't have the term xn, x1. So the expression is manifestly not translationally invariant. And indeed, UKW is not translationally invariant. The slightly surprising thing is that the product is translationally invariant. So you can drop the projection, then you are working with the invertible operator, which does not commute with the Hamiltonian, which is not translationally invariant. Alternatively, you can sacrifice the invertibility by multiplying the projection operator, and then you get something that's translationally invariant and commutes with the Hamiltonian. So you cannot, this is really unlike the projection case. Sorry, just 1 second. Yeah. It's really unlike the projection case, where in the projection case, you can work with the individual piece, and they are separately symmetry, but not in this case. Sorry.
You highlighted that this unitary operator doesn't commute with the Hamiltonian. Can you precisely say in which sense it fails? Like, does its conjugation just violate it or something?
Later on, I will give a derivation of this operator. In that derivation, you will make it clear why it does not commute with the Hamiltonian.
So in this case, okay, you convinced me that this way of writing it, it's not stupid and non-invertible as before, but wouldn't you need to prove that there is no way to write it as a sum of two things?
That's a fair question, and I don't think I have a good answer. But what I can rigorously show is that there cannot be a unitary operator that does this job. Yeah. That is a good question. Any other questions?
Is there a physical interpretation for this operator itself? So
Okay,
just for UKV, a physical interpretation?
There is. So it's related to David's question. So I will give a physical interpretation for it. I'm going to derive it right after. Any other question before I go to the derivation? Here I just put a lot of thin air. It's not supposed to be intuitive. It's supposed to be complicated. Then I'll explain the magic. Any other question? All right. Which blackboard I should use now? I want to keep that one. I want to keep this one. I guess I can drop this one. All right, so to derive this operator, I'm going to take a detour. It's a detour worth taking. And some of you might have already guessed the answer. Some of you might already say, oh, this is just the Majorana translation symmetry. But in the rest of the lecture, I'm going to explain what just means. So let's talk about a different model. It's a detour that we have to take, but when we get to the pion decay, you'll see that we have to take the same detour. And so I hope this exercise will be useful. So now I'm going to talk about a different model, Majorana chain. So I have a chain, but notice that I'm drawing the circle bigger than the one over there on purpose. Because now it's a chain with two end sides. And the factor of 2 is absolutely important. And I'm even using a different index label. Here I'm using little l, there I'm using little j. And again, it's a closed chain. And I'm going to identify L with L plus 2n everywhere. Now in this model, I don't have a local Hilbert space anymore at every site. At every site, I have a single Majorana fermions. So what do I mean by a Majorana fermions? The algebra is the following. So chi L is Grassmannian. And it obeys the Clipper algebra. Okay? So again, it's a finite dimensional problem. We have 2n Grassmannian variables satisfying the Clipper algebra. And all we are doing is just to write down some some representation for the Clipper algebra. And as everyone knows, I'm sorry. I need to stop. Oh, that's okay. So the Hilbert space, which I'll denote by H plus, the plus will be explained in just a few moments. So the minimal representation, the smallest irreducible representation for a 2n-dimensional Clifford algebra is 2 to the n-dimensional. So it has the same dimension as the Hilbert space over here for the Ising model. But importantly, I use a different notation. I call it H plus, because they are not to be identified immediately. So I give you the Hilbert space. I give you the local operator in this new problem. Now I'm going to tell you the Hamiltonian. So the Hamiltonian with a plus just nearest neighbor interaction between the Majorana fermions. So this model has a famous history. It is studied by Kitaev. It's called the critical Kitaev chain. Okay? All right. Now, on this model, what are the symmetries? There's also a Z2 symmetries, which I call -1 to the f. This symmetries is I to the n times chi1, chi2, all the way to chi2n. It's a product of all the fermions with a convenient normalization I to the n. The I to the n is inserted such that -1 to the f squares to +1. If you don't have that, you sometimes get -1, sometimes you get +1, and you have to worry about it. Now what it does is that it flips the sign. So here I should really write -1 to the f inverse, but because of the normalization, -1 to the f inverse is -1 to the f. And it's really awkward to write -1 to the f inverse. Okay, so it simply flips the sign of every fermion. It doesn't shift the fermion, you just flip the sign globally. So that's one symmetry, that's a Z2 symmetry. And you can easily see with naked eyes that this is a symmetry of the Majorana chain. There's another symmetry, which is the Majorana translation. So I'll call it T plus. Again, plus, the subscript plus will be explained in just a minute, where it shifts chi L to chi L plus 1. Okay, this is the lattice translation. It's obviously a symmetry. Okay, and this you can say is a Z2n symmetry, because T plus to the 2n power is 1. Now, if you go onto the street and ask a random person, they will say Majorana fermion is the same as an Ising model. This is a statement you hear every day. And if there's one take-home message from this set of lectures, is that that is simply not true. Majorana is not the same as Ising. And the difference between them is the non-invertible symmetry. If you don't distinguish Majorana with Ising, you are never going to be able to see the non-invertible symmetry. So how do you see that? There are two different models. Namely, the models on this blackboard is different than the model on that blackboard. Well, maybe for half of you, you don't even know that they are actually related. But for the other half, you might think they're actually equivalent. So I will try to address both questions. First, why are they different? The reason they're different is that in this model, you have a Z2n symmetry. You have a lattice translation that only goes back to itself. We erase it to the 2n power. But on that side of the blackboard, you don't have that. I only have a Zn symmetry. I cannot take the square root of my T Ising, however tempted I am. So the global symmetries are different. So there's no way that these two models will be equivalent. But what's the reason that you might think they are related? Well, that was answered by Jordan and Wigner from almost 100 years ago. And that's the famous Jordan-Wigner that we'll talk about. Any question about the Majorana model at this point? Just another many-body system in 1 plus 1D. Exactly solvable, and I have write down the two symmetries for you. Now, in the Ising case, we talk about the defect Hamiltonian because we have a Z2 symmetry. Here we can do the same. We have a Z2 symmetry that I call -1 to the F. So I can ask, what is the defect Hamiltonian associated with that Z2 symmetry? Here's my red. So I can consider a slightly different model. Where I flip the sign at only one link. Okay. Same Hilbert space, but different Hamiltonian. Now for this new Hamiltonian, I still have the -1 to the F symmetry, but now my lattice translation is slightly modified. It's not completely obvious why I will still have a lattice translation symmetry. After all, one side is different. But it's related to one of the questions asked in the previous lecture, that the position of this twist doesn't really matter. You can move it by unitary transformation. And because of that, you still have a lattice translation symmetry. Roughly speaking, shift L to L plus 1. I can put it in quotation marks because you actually have to flip the sign of one fermion at one turn, at one site. Let me not give the details. You can look at my Tassi lectures for the explicit expression. But roughly shift the fermions. Its 2nth power is no longer 1, but its 2nth power is -1 to the F. So those are just details. Don't worry about it too much. You can find the explicit matrix presentation or explicit expression of T's in terms of the fermions in my Tassi lectures. I'm not going to write it down here. Again, they are just matrices. Okay, so we have covered the Majorana problem. With either boundary condition, the periodic one with a plus or the anti-periodic one with a minus, you have a Z2 symmetry, you have a lattice translation symmetry. At this point, this just seems like a different problem than that. But there is a Jordan-Wigner transformation relating them, and that's what I'm going to talk about now. So the rough idea of Jordan-Wigner is that you can take a pair of the Majorana site. So you have chi1 and chi2, for instance, and the minimal irreducible representation for two Majorana fermions is two-dimensional. And that coincides with the qubit we talk about over there. The rough idea is that you can pair up the fermions and map the problem to the Ising model. So two Majorana fermions, roughly speaking, give you one Ising state. And the precise relation is the following. You can take chi 2j minus 1. Now I have to decide if I want to cheat a little bit. I want to cheat a little bit. Okay, so let's unpack these equations. So this is the famous Jordan-Wigner transformation. So we do a transformation on the Majorana fermions on the odd number of sites and on the even number of sites slightly differently. The difference is some minus sign, which doesn't really matter. The important difference is x versus y. So here, sigma x, sigma y, sigma z, they stand for the Pauli matrices. But notice that it's slightly different than the notation over there. And that importance is not terribly important. That difference is not terribly important, but we should still distinguish. Later on, we'll connect the sigmas to the x and z's over here. And here you see that J is the same labeling scheme over there. So, yeah. One important aspect of this transformation. Okay, first of all, let me say what this transformation is doing. The claim of Fenn of this transformation is that the sigma J, X, Y, Z, they obey the standard Pauli matrices anti-commutation relation. Sigma J at different sites don't commute with each other. At the same site is the standard Pauli matrix anti-commutation relation. So you use those anti-commutation relations that you know of on the right-hand side, and you try to compute the anti-commutation relation between the chi's up there. And the claim, which I'll leave it as a homework problem, is that that this equality is compatible with that anti-commutation relation. It's very easy to check, and it's really a beautiful formula due to Jordan and Victor. Okay. So far you can think about it just as a change of basis. We haven't done any physics yet. Now, one important thing about this formula is that from the Majorana problem, chi L is a local fermionic operator. It's centered at one site L. It doesn't commute with another fermion very far away. It anti-commutes rather, but that's just the nature of the fermion. The notion of locality is different for the fermions versus for the bosons. But if you try to express the fermions in terms of the bosonic spin variables, so I will refer to the Ising model as the bosonic models. I will refer to the Majorana model as the fermionic model. The point is that when you try to express something local in the fermionic problem in terms of the bosonic variables, it's no longer local. Here you see there's a product of the bosonic variables from J prime equals to 1 all the way to J. It's a string of bosonic variables. And this difference in the notion of locality between the fermion theory and the bosonic theory really lies at the heart of the non-invertible symmetry. But at this point, you can just view it as an identity in terms of algebra. Okay. So the next thing we are going to do is that we are going to substitute the chi's in terms of the sigmas in those two Hamiltonians and see what we get. Any question at this point? So far, there's no physics, as I emphasized. This is just a change of variable.
Is the inverse transformation easy to write down?
There is an inverse transformation, but I'm not going to write it down. You can, I mean, it's also on Wikipedia. But the important thing is that in the inverse transformation, the sigma, which is local in the bosonic problem, will be expressed in terms of a bunch of non-local fermions. Okay. So I'm going to write H plus and minus from the fermionic problem in terms of the bosonic variables. This is just a change of variables, as I emphasized, no physics. And what you get is the following. Let me comment that here minus 1 to the f, this this guy. And if you use this change of variables, you'll find that it's the product of the sigma z's. So you do this substitution into the Majorana fermion Hamiltonian, you almost get the Ising model. If you forget about the last term, this is almost the same as the Hamiltonian here. I'm just writing it in different notations, but otherwise they look identical. But there's one mistake you made, and one link on the entire lattice. You might think this is a very small price to pay. You can take n to be 1,000,000, and you only made one mistake out of 1,000,000 sites. But that makes all the difference on the non-invertible symmetry. So in most of the terms, it's completely local in terms of the bosonic variables. Now this is just a nearest neighbor interaction. This is completely local. But this term is not local. Minus 1 to the f is the product of the sigma z's on the entire chain. So this term is not local. And this is the point you fail. And this is the reason why the Majorana fermion is different from the Ising model. They are not related just by a change of variables. And to say how they are related exactly, you have to do something more globally to take care of this non-local term. And to really relate them, you can say we have to do a global Jordan-Wigner transformation. This one you can say is the local version. So what do we do globally? How do we fix this non-local term? Well, first, I would like to take you to a different Hilbert space. I would like to construct the following Hilbert space. So I have a Hilbert space, H plus here. I have an identical copy of the Hilbert space for the twisted Hamiltonian. They're isomorphic, but I just want to use a different notation. And here I'm just going to take the direct sum of two copies of them. Right? H plus and H minus, they're really identical. I just have different Hamiltonians. And I define a bigger Hamiltonian in this block diagonal form. Okay? So everything with a tilde will be on this bigger Hilbert space. So this bigger Hilbert space is 2 to the n plus 1 dimensional. And then from here, I'm going to do a projection. I'm going to define this Hilbert space H, which coincides with the H up there. By doing this projection. So what did I do? I first double the Hilbert space by taking the direct sum. And then I do a Z2 projection. So I reduce it by a factor of 2. I increase it by a factor of 2 and then decrease it by a factor of 2. So at the end of the day, this Hilbert space is 2 to the n dimensional. What is the projection I'm doing here? So I have a minus 1 to the f in each copy of the Hilbert spaces. In one one copy of the Hilbert space, I project it to the minus 1 to the f even sector. In the other sector, I project it to the odd sector. And why do I choose this plus and minus? It's because in the minus sector, I have a minus sign here. Right? And if I project to the minus 1 to the f equals to plus 1 sector, this minus sign agrees with the rest of the minus sign. If I were in the H plus sector, I have a plus sign here. And putting minus 1 to the f being minus 1, in total I have a minus 1 here, which also agrees with the minus sign for the rest of the terms. So in doing so, this big Hamiltonian ends up looking like the one here. And I took care of the non-local term by doing this projection.
When you do the projection, is the new Hilbert space still tensor product Hilbert space?
Good. So the original Hilbert space is only tensor product when you pair up the terms. The new Hilbert space is a tensor product Hilbert space in terms of the new bosonic variables by construction. Because you literally end up with this original transverse field Ising model. Okay? So it's quite a long detour. We start with a Majorana problem. We consider two kinds of boundary condition. We enlarge the Hilbert space, we do the projection, and somehow we land on our feet. We retrieve the Ising model, the original bosonic problem. Now the reason I use sigma here and x there is because the difference is somewhat minor. It's because we enlarge the Hilbert space, we do the projection, so they are not exactly identical, but you can map one to the other. So let me not spell out the details. Okay, so why do I go through all this exercise? 20 minutes.
Before you do this enlarge projecting,
Right.
if you would identify the sigmas with the corresponding x and c,
Right.
wouldn't you get the defect Hamiltonian?
No. You see, the defect
G not an eta. I'm sorry.
Yeah, it's just flipped. Yeah, there's no. I mean, everything is local in the defect Hamiltonian. The question you could have asked is, here this is the new Hilbert space, and my H tilde will restrict to this projected Hilbert space. Is the H up there? But you could have asked, how do you get H eta? And there's an alternative projection you can do. You just flip the sign to be -1 plus 1. So you get both the Z2 twisted and the untwisted Ising model. Yeah.
Can you give all as a GSO projection?
Yeah.
Okay.
Yeah, it is. It's the lattice version of the GSO projection. It's the lattice version of doing bosonization. Now, why do I go through all this? The reason I go through all this is because I want to see what happens to the Majorana translation operator. The Majorana translation operator is the mystery in the relation between Majorana fermion and the Ising model. Why was it a mystery? It was a mystery because we had a Z2n symmetry in the Majorana problem, but we didn't have any Z2n symmetry in the Ising model. But now that I have established a relation between the Majorana problem and the Ising problem, you can ask, what happens to that Z2n Majorana translation symmetry as you go through this whole enlarge and projection process? So let's do that. And that will reveal for you the non-invertible symmetry. Okay. Every blackboard is simple. Okay, so before we do that, let's first observe two very interesting properties of the translation operator. You see, here we are going to do a projection in -1 to the f. So I better know the algebra between -1 to the f and the Majorana translation before I proceed. So let's do that. It's actually very easy to do. So I'm going to compute this algebra for you. Okay. This is very easy to do because I told you the explicit expression for the Majorana for the -1 to the f. I didn't write down t plus explicitly for you. You can see my Tassi lecture. It can be written down in terms of the chi's. It's a little bit complicated, but not too complicated. But we don't need that. I only need this relation. So when I do this conjugation on the -1 to the f, what's going on? 1 goes to 2, 2 goes to 3, 2n goes to 1. But I want to compare it with the original -1 to the f. So what do? I move the last one step by step to the beginning. I have even number of fermions here. So there are exactly odd number of fermions between this guy and the first position. So I get a minus sign when I move this chi1 back to here. and try to write it in terms of the minus 1 to the f. So if there's a single most important minus sign in the whole story, it's going to be this one. Again, this is just the commutation or anti-commutation relation between matrices. It's really, you can really see it, you can really do it in real time. If you don't believe me, you can also write both of them in terms of matrices and check it for yourself. That's in the periodic sector. In the anti-periodic sector, I didn't tell you the details here. I put a quotation marks. And there's an extra minus sign, as you can imagine. So let me skip the detail. So maybe you can take my word for it that the minus sign disappears. It's basically because when you try to define T minus, you have to flip the sign of the fermion at one side. So there's a minus sign here, there's no minus sign there. Now we can come back here to see what happened to them. Now, I would like to define operator T tilde. Again, everything with the tilde is on the bigger Hilbert space. So I'm just going to define it in the same way I define the Hamiltonian. So I put T minus here, I put T plus here. It's an operator acting on H tilde. And there's nothing wrong with that. But then in the next step, this is only the first step, right? Remember, the first step is to enlarge the Hilbert space. The second step is to do the projection. So I succeeded so far halfway through. But in the second step, I will run into trouble. Because when I do the projection, I found out that minus 1 to the f does not commute with T plus, right? Because of that minus sign. So what does that mean? It means that T tilde does not act within this projected Hilbert space. Right? You start with a state in this projected Hilbert space, you act with T tilde, it takes you outside that projected Hilbert space. So T tilde cannot be restricted to this 2 to the n dimensional Hilbert space. And that might be the end of the story. Now we realize that, oh, okay, so that's the reason why Majorana translation symmetry does not become a symmetry in the Ising model. And that makes sense because we don't have a Z2n symmetry in the Ising model up here. And this projection explains why you don't have that. So you can do something better. One thing you could do is to consider this out. You put a square. The square of a minus sign is a plus sign. So this operator, you can't restrict it to the projected Hilbert space because that minus sign that bothers you before is no longer there. So I can define it to this projected Hilbert space, and not surprisingly, that's the Ising translation operator. So you cannot do this, but you can take the square, and then it survives the projection. And that is nothing but this operator. So you do have a Zn symmetry, not Z2n, but you have a Zn symmetry. Okay? All right.
I have a question.
Yes, please.
So you see how like you recover H from like just two copies of the periodic and anti-periodic?
Yes.
I go back. So if I start with the bosonic sector.
Excellent question. You could. It's related to the inverse transformation, which I'm not doing. But if you want to go back, you take H and H eta.
Yeah.
Any other question? Good. So let's get to the punchline. The punchline is that you can do something better. And I need to decide which part of the blackboard I'm erasing. Maybe I'll erase that. The thing that causes us trouble is this t plus. That's where the minus sign came from. But t minus is fine, right? You shouldn't blame t minus. Let's put the t minus there. Now t plus was causing us trouble, so we're just going to put a 0. Right? That's an operator you can consider. And now it does survive after the projection, because we just simply set the problematic term to be 0. So I can do the projection. And I'm just going to call this operator B. And that is the operator we started with. This operator, it acts as a Marwana translation only in half of the Hilbert space. But it acts as 0 in the other half. And the 0 we gave it there, almost superficially or artificially, is the reason why it's non-invertible. Because of the 0, it has a big kernel. But you see that this obviously is a symmetry of the Ising Hamiltonian at g equals to 1. Because each individual, the 0 obviously is a commutes with the Hamiltonian. And this piece we have already established is a symmetry of H minus. So D, after the enlargement and the projection, is again a symmetry of that at the critical point. We also explained why D times eta is D. Because eta here, roughly speaking, is identified with minus 1 to the f there. There is some qualification to that. But eta is basically making plus 1 here and minus 1 there. You have a big 0 there. So multiplying by eta doesn't change it. You also make the algebra d times d equals to t Ising times the projection object. Because d times d is just t minus square 0, 0, 0. And that is t Ising times the projection to the upper left block. All right. So that's all I want to say about the transverse field Ising model. We started with the bosonic problem without knowing any fermionic background. We go to the critical point at g equals to 1. I pull it out of thin air that there's an additional conserved operator d that obeys this algebra. This you can check by hand, by brute force. You don't have to know any fermions, it's just about matrices. But to really understand the origin of this operator, you have to go through the Majorana fermion. There's actually also a bosonic way to understand it, but let me not say it here. That's related to one of the 6 constructions I gave at the beginning of the last lectures related to half gauging. You can see that at the end of the day, what do you have? You have an operator in the bosonic Ising model. It's trying its very best to be a half translation. Right? It squares almost to a full translation, but not quite. It's only in the Z2 even sector. And this projection makes it non-invertible. If you erase any part of if you erase this part of the formula, don't worry about it too. This formula exists in the continuum CFT, and that has been studied beaten to death in the literature. If you erase this part of the literature, the formula, then that's just saying that D is roughly a half translation. But the fun part is that it's really the combination of both that appears as the symmetry algebra of the transverse field Ising model. 5 minutes left. We started around 10:20. Okay. Any question?
Not so strict here.
Okay. Any question about the transverse field Ising model? Yeah.
So you mentioned you would explain this long unitary operator from before. Is it that it's like a square root of the t Ising? Is that?
Yeah. The u. Where is it? Yeah, it's basically this guy over here.
It's just u total.
This guy. This is invertible, right? Basically, yeah. Any other question? Okay. All right, so this is one example of the non-invertible symmetry. At the end of the day, it's just a matrix you can write down. And it commutes with the Hamiltonian, you obey all these nice properties. Let me make a quick connection to the continuum, which might be more familiar to some of you. So how do you phrase what we just did in terms of the continuum? In the continuum, on the one side, yes. Yeah.
For clarification, no? Like eta is minus 1 to the f 0, 0, minus 1 to the f restricted to the projected Hilbert space.
That's right.
Okay.
That's right. Here I'm being a little bit sloppy because
when you write 1 plus eta half,
yeah.
that becomes just 1, 0, 0, 0. So
That's right.
That basis.
That's right. That's right. That's right. That's right. That's right. To be more precise, on the bigger Hilbert space H tilde, you have two symmetries. Right? You have minus 1 to the f, minus 1 to the f. And you have another symmetry, which is just 1 minus 1, 0. Okay? And I can call this minus 1 to the f, tilde maybe. This I can call it eta tilde. This is on the bigger Hilbert space. And the projection, so we have a Z2 cross Z2. By the way, this is the categorical symmetry that Shao likes to talk about. There are two Z2s on the bigger Hilbert space, but not in the smaller Hilbert space. And the projection is to restrict to this. So you take your Z2 cross Z2, and you set one of the Z2 to be plus 1. You do the projection with respect to one of the Z2. And in this restricted Hilbert space, eta becomes identical to minus 1. So this so thank you for the question, because this actually is connected to the sync TFT story in a nice way. Okay, so maybe the remaining 2 or 3 minutes, let me say a little bit about how to think about all this in the continuum. In the continuum, we can talk about the Majorana CFT. So what is the Majorana CFT? It's a CFT that has the following Lagrangian. So you have a left-moving Majorana field. You have a right-moving Majorana field. And this is just the standard Weyl action or Dirac action in 1 plus 1p. It's massless. On the other side, you have the Ising CFT. The Ising CFT, there are several different ways to think about it. It's the simplest minimal model, or you can think about it as the critical point of the Landau-Ginzburg 5-4 model. Local operators are the identity operator with conformal weight 0, 0, H and H bar, and then epsilon, 1/2, 1/2, and sigma, 1/16, 1/16. Now, what are the global symmetries? The Majorana CFT has 2 internal global symmetries. There's a minus 1 to the f that map pi left to minus pi left, pi right to minus pi right. There's a minus 1 to the f left that map pi left to minus pi left, pi right to pi right. Obviously, you can compose the 2 generator and get minus 1 to the f right that only flips the sign of the right-handed fermion. But in total, you have Z2 plus Z2. Okay? On the Ising model, you have an invertible Z2 symmetry that takes sigma to minus sigma. That's what we do. Identity operator obviously is Z2. If you open any standard CFT textbook, they will tell you the Majorana CFT is the same as the Ising CFT. And as I emphasized, that is not true. And the easiest way to say that is that their global symmetries are different. Ising model, no matter how you look at it, has only one Z2 symmetry. It's the Z2 that flip, or erase it, flip all the spins on the lattice, and that's it. You don't have the second Z2. Majorana CFT, on the other hand, have two Z2. One Z2 that flip the left, the other that flip the right. And the fact that they have different global symmetries means that there are two different CFTs. How is this compared to the lattice model we just discussed? This Z2 is just the eta we talked about in the transverse realizing model. This minus 1 to the f is the same minus 1 to the f of the Majorana problem. This minus 1 to the f left is more subtle. It comes from the lattice translation. So on the lattice, you have a translation operator that moves the Majorana fermion from one side to the next. It's not an internal symmetry, it's a spatial symmetry on the lattice. But it mixes, when you take the thermodynamic limit, it mixes with the continuum internal symmetry. And this is something very common in condensed matter physics. It has been called eminent symmetry in some recent literature to be distinguished with the emergent symmetry. Let me not say too much about it. It's just a phenomenon where, in this case, it's a lattice translation that mixes with the internal symmetry of the continuum CFT. Okay. Now, the relation between the two CFT is that you can start with the Majorana CFT, and as someone already pointed out during the lecture, you can do a GSO projection to get an Ising CFT. And what that means more precisely is that you gauge minus 1 to the f. As you gauge minus 1 to the f, by definition, minus 1 to the f is no longer a global symmetry after gauging. Right? You promote the global symmetry to a gauge symmetry, so it's no longer a global symmetry. But in 1 plus 1D, whenever you gauge a Z2 symmetry, you lose one Z2 symmetry, but you gain another symmetry back. That in the literature is known as the quantum symmetry, the orbital symmetry, the dual symmetry. It has a lot of names. So eta here is dual to the minus 1 to the f. I can explain more about what dual means, but I probably won't have time. I'll just say in one sentence. It means that eta, the symmetry operator for eta, is the Z2 Wilson line of the gauge minus 1 to the f. Okay, that's a short sentence, but it has a lot to be unpacked. So let me just the more interesting thing is what happens to minus 1 to the f left. There is a mixed anomaly between the minus 1 to the f and minus 1 to the f left. This anomaly is very famous. It's a Z8 anomaly. This 8 is also the same reason why superstring theory lives in 10 space-time dimension. The arithmetics is that you start with 10, and you do the Lycombe quantization, meaning that you do some gauge fixing, there are some constraints, so 10 minus 2 is 8. It's the same algebra you do in real world. The gauge field of the real world, A mu, has 4 components, but you only see 2 polarizations. Right? There's a clockwise polarization, there's an anti-clockwise, counterclockwise polarization. And the reason I go from 4 to 2 is because of the gauge symmetry. In superstring theory, you start with 10 fermions on the worksheet. You do Lycombe quantization, you get rid of 2. And 10 minus 2 is 8. And take my words, that's the same 8 here. There's a mixed anomaly between the two. The definition of mixed anomaly is that if you gauge one, the other becomes weird. Now, how weird it is? The statement is that it becomes the non-invertible symmetry. And we saw that explicitly how it works on the lattice. On the lattice, this -1 to the f left starts as its life as a Majorana translation operator. And when we gauge, or when we do GSO, that's the song and dance we did here. We enlarge the Hilbert space, we do the projection. This two steps process is exactly the same on the lattice and in the continuum. And you saw exactly in what sense it becomes weird. The weird guy is this guy. This guy doesn't survive the projection. And that's the signal of the anomaly over here. But it's not completely gone. There's something that can be resurrected. And that's by putting a 0 here. But the price you pay is that it becomes a non-invertible symmetry in the continuum Ising. All right. I guess I'll just stop here. And yeah, so in these two lectures, we cover the lattice Ising model and a little bit about the continuum Ising model. And this is really the simplest example of the non-invertible symmetry. Okay, I'll stop here. Thank you.
I have a question which is precisely about the factor of 1/2. So at the beginning of the previous lecture, you said that the factor of 1/2, in general, you have to be careful because you cannot divide Hilbert space. So I guess then here this makes sense because you're doubling and then projecting somehow, but
That's excellent. So I have to say, so I emphasize on the lattice, this relation between operator and defect is not transparent because you cannot do Vic rotation that easily. And that's still something I would say is an open question on the lattice. That is there a preferred normalization of such non-invertible symmetry operator on the lattice? In the continuum, you cannot arbitrarily divide it by 2 or 1/√2, etc. On the lattice, it's less clear. I believe the answer is that we should have divided by a √2 so that you don't have the factor of 2 here. But that requires more information. That requires you to compare this non-invertible symmetry operator with the non-invertible defect on the lattice, which I didn't tell you. So you see, there's an obvious gap in my presentation. When I talk about the Z2 symmetry of the Ising model, I immediately told you, I wrote down the operator, and I also wrote down the defect Hamiltonian, the H eta. I wrote down eta as an operator, and then I wrote down H eta, the defect Hamiltonian. For the non-invertible symmetry, I wrote down D in excruciating detail, but I didn't tell you what H sub D is. I didn't tell you what the defect Hamiltonian is. And I believe the relation between the two would fix the normalization for you, but I didn't do that here. Any other questions? Yeah.
Is the fact that this Z2 symmetry gets mapped to a non-invertible symmetry, is it related to the fact that it has an anomaly?
Yes. So it's a general feature, that phenomenon that back in the days, people thought when you have a mixed anomaly between two symmetries, A and B, if you gauge A, that means B is broken. It's gone after you in the gauged theory. But nowadays, we saw more and more examples where that is not the case. It's quite common that when you gauge A, B becomes a generalized global symmetry. It's not always true, but it's true in many cases, especially for discrete gauging. And here we saw one example, where the anomaly turns the invertible symmetry into a non-invertible one. There are also other examples where the mixed anomaly turns the invertible symmetry into a higher group symmetries. Any other question? Well, if not, I guess we can go to the break, and I'll be happy to answer more questions during the break. Yeah, if you have any. Thank you. So yesterday we talked a lot about Ising model, and that was in 1 + 1D. And for the next 3 lectures, we'll go to higher dimensions. And by higher, I mean greater than 1 + 1. dimensions, the construction of the non-invertible symmetries is relatively new. So do a schematic diagram. So if you think about the ordinary symmetry as an origin in some two-dimensional plot, there has, for some time, there seems to be two orthogonal generalization of the global symmetry. In one direction, you can make it non-invertible, as we saw in the Ising model yesterday, but that was mostly in two space-time dimensions. And even though we didn't say anything about other examples other than Ising model, in two-dimensional rational conformal field theory, there are a lot of examples of non-invertible symmetry. In almost every rational conformal field theory that I know of, there's a non-invertible symmetry. So in two space-time dimensions, it seems really ubiquitous. On the other hand, as you go up in dimensions, you have more options in space. You can have line operators, surface operator, etc. And then you can have global symmetries acting on various defects of different dimensionality. And that opens the door for higher form symmetries. Higher form symmetries are in many ways boring in E equals to 2. I mean, there are higher form symmetries in two space-time dimensions, but they would necessarily lead to generate vacua when you quantize the theory on the circle, and that is known as the decomposition. But if you assume you have a unique topological local operator in two space-time dimensions, then you don't have any higher form symmetry. On the other hand, for some time, we only have interesting examples of non-invertible symmetries in two space-time dimensions. So in many ways, it would really look like two orthogonal generalization of global symmetries. Now, having said that, it's actually very easy to construct non-invertible higher form symmetries in general dimensions. And one thing you can do is in general dimension, you can start with a zero form symmetry G, and you gauge it. And as discussed in the discussion session by David yesterday, once you gauge G0, what you get back is a graph G symmetry. Now, that might look a little bit fancy, but in physics terms, it just means that these are symmetry. A symmetry is generated by the Wilson lines. Now, we are familiar with Wilson lines in continuous gauge theory. In continuous gauge theory, Wilson lines are not topological. It costs you energy to separate two Wilson lines. Wilson line describe the war line of some heavy electron in QED. But if G is a finite group, then the Wilson lines are topological, and then they can be viewed as the symmetry generator for some higher form symmetry, which I will say a little bit more later on. More specifically, it's a D minus 2 form symmetry. And when G is a non-abelian finite group, the corresponding higher form symmetry will be non-invertible. Now, I don't want to say too much about the non-invertible higher form symmetry in this talk, but in a way, they are easier to construct. But for some time, it wasn't clear if there were non-invertible zero form symmetry. And by zero form, I just mean ordinary symmetries that have some local operators that has support over the entire space. So in the next 3 lectures, I will talk about some developments from 2021, where people have figured out how to combine non-invertible symmetry and higher form symmetry to construct many interesting examples of non-invertible symmetries, in particular non-invertible zero form symmetry in diverse space-time dimensions. And they're also realized in many realistic examples. Examples in QED, in free Maxwell theory. We also have examples in axion physics, and string theory, M theory, and the list goes on. Okay. So that's just kind of an overview of what we are going to do in the next 3 lectures. So to proceed, we should first say a little bit about higher form symmetry. Now this might be a subject that's very familiar to some of you, but for completeness, let me still give a lightning review on what the higher form symmetries are. So let me do the case of a U1. In relativistic quantum field. In that case, the starting point is a Q plus 1 form. You can also dualize it to view it as a D minus Q minus 1 form. So let me work with this convention. So it has Q plus 1 indices. This is a local operator, it's a current. I might just denote it as J. Now it satisfies the conservation equation. Or if you write it in terms of the differential form notation. So here, you shouldn't question where it comes from. The starting point is that we have such a local operator in my relativistic quantum field theory in these space-time dimensions, and the starting point is that it obeys this conservation equation. In taking this as an assumption, let's see if we can construct any conserved quantity. That's the name of the game. In fact, this is the same strategy we will apply later on when we talk about non-invertible symmetry in QED. In just a few moments, I will give concrete examples so that it won't look so abstract. Now, taking this as the starting point, you can easily write down a conserved charge. Oh, I should mention that when Q is 0, that's a 0 form symmetry, and that corresponds to the ordinary symmetry case, where your Noether current is a 1 form or a vector. Now, a conserved charge in this case can be defined on a general D minus Q minus 1 form. D minus Q minus 1 dimensional manifold, closed manifold in space-time, by taking the integral of star J, and the unitary operator that implements the symmetry, the unitary symmetry operator. So generally, I would distinguish, here's one comment on the terminology. By charge, I meant the integral of the current, and it's something in the exponent. By symmetry operator, I mean the operators that's, in the invertible case, that's unitary and act directly on the Hilbert space. Now, since the charge is supported on a higher codimensional manifold now, the object that the higher form symmetry act on is different from the case of the 0 form symmetry. The way it acts is that in Euclidean space-time, another object, an extended object, it could be a Wilson line, for instance, that's supported on a Q-dimensional manifold. By the way, that's the reason why this is called a Q-form symmetry. It's because the charged object is Q-dimensional. You might be wondering at this up to this point, where's the number q? Why is it always q plus 1, d minus q minus 1? Where's the number q? Why don't we shift the definition? The reason is because you want the charge object to be q-dimensional. You also want everything that's ordinary corresponds to q equals to 0. So that's the naming scheme. The charge object now is q-dimensional, and the way that the higher form symmetry acts is by linking. So if you have a d minus q minus 1 dimensional manifold and a q dimensional manifold, they can link in these space-time dimensions. Like in the picture I'm drawing, d is 3, q is 1, and therefore this is 1. That's why it's a loop. Q is 1. That's why the charge object is also a line. And two one-dimensional objects can link in three-dimensional space-time. And that just gives you, let's say the charge object has charge n, and the action is just given by e to the I n theta times wn. All right. So that's all very basic. I hope most of you have seen some version of this in the past. And just to make you bored even more, let me quickly say the simplest example of a one-point symmetry, which is something we actually learn in undergraduate electromagnetism. But this example will be important later on when we construct a new non-invertible symmetry. So take the example of the 3 plus 1D, namely the real world U1 Maxwell field. The H field is a one point. We have the gauge and the gauge transformation is this, and the gauge invariant field strength is F mu nu, which is the exterior derivative of A. And the Lagrangian is just one comment is that I put the electric coupling as an overall factor in the Lagrangian in such a way that all my gauge fields are properly quantized. They are properly quantized, meaning that if you take this 2 form and integrate it on any 2 manifold, this is known as the magnetic flux in physics, you get 2 pi times the integer. If you are a particle physicist, you sometimes use a different normalization where you rescale E into your definition of the gauge field. That will be more convenient when you do perturbation theory. But here most of the discussions here are about global aspects of the theory, including symmetries, and it's more convenient to normalize your field this way. All right. So that's the free Maxwell theory. It's quadratic in the gauge field. It's a free theory. So unlike the Yang-Mills theory, this theory is free, it's completely solvable. And yet, there are new symmetries of this model that were only discovered around the time of 2021. So that will be the subject in the next lecture. But in this lecture, let's just set up some formalism behind the U1 Maxwell theory. So U1 Maxwell theory has 2 one-point symmetry. It has a U1 one-point electric symmetry. The superscript is there to remind us the form degree of the global symmetry. So one-point symmetry, that's why I put the 1. The subscript E will be explained in just a moment. It's just a label. It also has a magnetic one-point symmetry. There are also some ordinary zero-point symmetries. For instance, there's the parity. There's also a charge conjugation symmetry. But let me not talk about it. You can say these 2 one-point symmetries are also new symmetries of the Maxwell theory. But in many ways, they are kind of just the one-point symmetries here are just rephrasing some of the known phenomena that we know of into this generalized global symmetry formalism. The higher point symmetry become very powerful when we go to non-abelian gauge theory, and there could be anomalies between higher point symmetries and other symmetries. But that would not be the focus on the top of it. Let me just tell you what these two symmetries are. So if you take the definition there, the name of the game is to identify some local operator in the theory over here so that it obeys this conservation. That's not too difficult. You take the Lagrangian over there. You can take the field variation with respect to the gauge field and find the equation of motion. Now the equation of motion just tells you B star F, E mu F mu vanishes. Remember, this is the pure Maxwell theory. We don't have any dynamical charged matter fields. We don't have electron. We don't have any charged scalar fields, etc. That's why on the right-hand side it's just 0. From the equation of motion, you immediately recognize that you can view F here as an example of such a current. F has 2 indices, and that matches with Q equals to 1 over here. So this leads us to identify a 2-form current as just F. Well, let me make a comment that some people prefer to define the current with an extra Hodge dual. In many ways, that's actually better. But for pedagogical reason, I always find it easier to define the current in this way, so that when Q is 0, the Noether current is a 1 form rather than a D minus 1 form, which is usually how it is presented in standard quantum field theory textbooks. Now, in 4 dimension, it's a fortunate fact that 2 equals 4 minus 2, so it doesn't make a difference for 1-form symmetries. But in some papers, you might find an extra Hodge dual over here. Now, there's another subtlety, is that sometimes you might prefer to normalize your JE slightly differently by a factor of E squared. And that has to do with how you properly quantize the electric flux. So let me do that. It's actually 1 over E squared. Maybe there's a factor of 2. Let me not care about the factor of 2. Now, given such a current, you can then define. Let me not do it, because I didn't really say how the charge are quantized. So given such a current, we follow the same procedure. You pick a 2 surface, and you integrate star F. Now this has a name. This is something we all study in undergraduate electromagnetism. That's just the electric flux. So you can take sigma 2 to be a 2-sphere in space, like a literal 2-sphere, nothing fancy. And you can imagine you are measuring the electric flux coming out of this sphere. Now there's one point I would like to clarify, because you might be puzzled by this point. We said we are dealing with the free Maxwell theory. So where does the electric flux come from? The photon doesn't carry any electric flux. So what is this 1-form symmetry is trying to measure? The idea is that we don't have any dynamical electron fields in the Lagrangian. We didn't add any phi or psi to this Lagrangian. We didn't do any path integral over those dynamical fields in the Lagrangian. However, you can still contemplate the existence of some very heavy electrons sitting at some point in space, but it's extremely heavy that you are not supposed to path integrate it over anymore. So there are like some probe defect in your theory. Then you can introduce them into your Euclidean configuration. The war line of a very heavy electron, well, it's a one-dimensional object in space-time. It extends in the time direction. It sits at a point in space. And those are the things that the 1-form symmetry tries to act on. Remember, when Q is 1, the charged object is one-dimensional in space-time. and they are exactly the war line of infinitely heavy electron. But they are not dynamical because they are so heavy. They don't fluctuate. And the only and the one-point symmetry measures is the electric charge. One thing I forgot to mention over here is that why is this a conserved charge? The reason that it's a conserved charge is because star J is a closed form. By Stokes' theorem, it means that the value of Q will be independent of small deformation of M. And in particular, if you deform it in the time direction, any observable will not change. So more generally, it gives you a topological. Now, topological might sound like a fancy word, but in the case of E and M, it's literally the Gauss law. The next time you want to explain to your friends what topological means, really the Gauss law is the best example. And we all understand what that means in this particular context. If you have some very heavy electron sitting at the origin in space, and you want to measure the electric flux, you can surround the electric flux by a sphere, or alternatively, you can surround it by a cube. And Gauss's law told us that it doesn't matter what's the detailed shape of the Gauss surface. No matter which surface you pick, as long as it contains the sense number of electric charges, you get the same integral. So in that sense, it's a conserved charge. As you can see, so far, there isn't really any fundamentally new physics. We kind of just repackage what we used to know as the electric charge into a new language in terms of a global symmetry charge. But it actually buy you a lot down the road. The general idea is that, you see, throughout this whole the 5 lectures, we're talking about global symmetries. Global symmetries are symmetries that act on the states, that act on the operators. This is to be contrasted with the gauge symmetry. Gauge symmetry should be thought of as a redundancy of the description of the system. But the moment you said those words, you get confused, because when we learn undergraduate electromagnetism, we learn the concept of gauge charge. What is gauge charge? If gauge symmetry is supposed to be redundant, how do we even define gauge charge in an invariant way? This question might sound a little bit academic in 3+1D, but it gets more serious when you go to more general system. And let me make a quick comment. If you go one dimension lower to 2+1D, you can write down the same level. But a 2+1D photon has only one polarization. So how do you understand that? If you have a gauge field in 4D to start with, you have A mu has 4 components. But the gauge symmetry eliminates 1 degree of freedom. There's an associated constraint, the Gauss constraint, that eliminates the other. So you end up with 2 degrees of freedom. That's something we're all very familiar with. If you have a photon propagating that way, you can have a polarization going clockwise and another polarization going counterclockwise. So the important formula here is 4 minus 2. If you go down in 1 dimension, you start with 3 components. But the subtraction is the same. You still only have 1 gauge symmetry. The gauge parameter is still a scalar. So the number of propagating degrees of freedom in 2+1D for a photon is 1, because 3 minus 2 is 1. Okay, what other fields have 1 degrees of freedom? A scalar field. And it is a true fact that in 2+1, so let me make a little box here. If you are in 2+1, a free photon is dual to a scalar field. More precisely, a compact scalar field. And if this is the first time you see the equivalence, this is known as a duality. It means that it's the same underlying quantum field theory, but it emits 2 seemingly different descriptions. If this is the first time you see the duality between a photon and a scalar in 2+1D, you should be shocked. Because we were brainwashed that gauge symmetry should be the fundamental language for describing our nature. But if you take a 2+1D system, we immediately realize that's not the case. In one description of the theory, in terms of F mu nu of the photon, you have a gauge symmetry, which takes identical form here. You just think about it as a differential form in 2 plus 1. But in the other description, it's literally just a free scalar field. And there isn't such a gauge symmetry in a free scalar field. There are more general kinds of dualities like this in 2 plus 1D, especially in the context of condensed matter physics, and that goes under the name of particle vortex duality. So it is extremely common that in theoretical physics that you have dualities where on the one side there is a gauge symmetry, on the other side there isn't. And that underlies the fact that gauge symmetry cannot be fundamental. But then it begs the question that what do we even mean by the gauge charge of a particle? This is a term that we are so used to that we talk about it every day. We talk about the electric charge of the electron. What does that even mean? And that's where the generalized global symmetry, or the higher forms global symmetry, make it precise. Here we interpret QE, the electric charge of a very heavy electron, as a one-form global symmetry charge. And the emphasis here is really on the word global. And I should say that here, throughout the whole lecture, by global, we don't mean a charge that acts globally on the entire space. It's a very unfortunate terminology. Global should be defined as non-gauge. It's actually used to be contrasted with a gauge charge or gauge symmetry. Just 1 second. So the upshot is that one of the motivations for using this new language of higher form global symmetry is that now you can meaningfully talk about the gauge charge in terms of a global symmetry charge. And in the case of the particle vortex duality, on the one side, the gauge charge is interpreted as a one-form global symmetry charge of some electric one-form symmetry, and there's an analogous statement on the other side for a free scalar field. But now that everything is phrased in terms of a global symmetry charge, they are matched exactly under duality. And you don't have to be worried that if you are working in a duality frame, there's a gauge symmetry or not. Sorry, there was a question.
Yes, so when I hear the words about the electric charge of the electron, I thought this meant the charge under the, so you take the gauge transformation to be a constant at infinity, and then this also a global symmetry, but this would be a zero form symmetry. So what's the relation with?
I think that's always an ambiguous statement. I think it's true to some extent, but I don't want to make too much commitment to that. And let me make a more general comment. Throughout the whole lecture, I try to work in compact space-time. You see, in the Ising model discussion yesterday, I made it very clear by drawing a big circle at the beginning of the section to emphasize that we work on a closed chain. And in a way, I think that's one way to proceed. You start with compact space. And then if you eventually want to go to infinite space, you take a limit of that. But we first want to understand what's going on in compact space. Now in compact space, I wouldn't have to address the question you asked, because there's no infinity. You don't talk about the asymptotic gauge symmetry or whatsoever. Then you can ask what happens to infinite space. You can view it as a limit of a compact space result. That's generally how I think about it. There are alternative approaches to understand symmetry by working directly on infinite space. And that's kind of a whole different philosophy. It gives a lot of amazing results, but at the moment, I think it's an interesting open question to how to bridge the two sets of, two different approaches. So for my lectures, I will work in compact space where many things can be made very precise. Sometimes it might get complicated, sometimes it might get complicated, but at least it's very precise. And I do think it's worthwhile to think, to understand how this perspective is related to the infinite space result. Any other question? All right, so that's, oh wait, there was a question? Oh, sorry.
I'm not quite sure if you addressed it and I just misunderstood, but in that duality, how do I think of the Wilson lines on the
Yeah,
scale?
well, I didn't explain, so I was trying to skip that. Yeah, so this is a compact scalar field. I should really emphasize that. It means that the scalar field phi, I'm sorry, this is really small, but it's not going to be too relevant for the rest of the lectures.
Compact, you mean target space S1.
Yes, sorry, by compact I mean the target space of the scalar field is a circle. And here I normalize the circle to have 2 pi periodicity. And you can move the periodicity to the okay, so the target space is a circle. And therefore, when your actual space has a non-trivial cycle, your scalar field can wind around that spatial circle. And that will create a vortex. And the vortex is an object that's one-dimensional in space-time. So you should think about it as a very heavy particle. And if you go around the vortex, your scalar field will wind. And that vortex is the Wilson line, the dual picture. And the winding number is the electric charge. Any other questions? Okay. Now, similarly, oh, and let me make another comment. One way to break the one point, so if you have ordinary 0-point global symmetry, to break it, you introduce an explicit local operator to the Lagrangian. If you have a Z2 global symmetry, add a Z2R local operator to the Lagrangian, that explicitly breaks it. That's not the case for higher form symmetry. Higher form symmetry, they act on extended objects, such as Wilson lines. So to break it, you cannot add a term to the Lagrangian. Rather, they will be broken. And here by broke, there was a question yesterday asking what break means. Here, I mean explicitly break the symmetry by some mechanism. To explicitly break the one-form symmetry, what you will do is to introduce a dynamical charged object. It could be a Dirac fermion, it could be a scalar field. As long as it's charged under the gauge symmetry, that will do the job. Indeed, if you couple the gauge field to some additional matter, which we will do in the final lecture, it won't be a 0 on the right-hand side, and therefore you lose the conservation. This is the electric one-form symmetry. There's also a magnetic one-form symmetry. And the equation associated with the magnetic one-form symmetry is just the Bianchi identity. You just remove the Hodge dual. The magnetic charge is and then the conserved charge for this magnetic one-point symmetry is just the magnetic charge. And to break it, you have to introduce a dynamical, magnetically charged object, a monopole. So the two symmetries are exactly parallel to each other. You just exchange the adjective electric to magnetic, and that underlies that highlights the electromagnetic duality of the two. Okay. That's a lightning review of the higher form symmetries. Let me see what do I want to do next. Let me do one more example. I'm not sure how much much I should talk about higher point symmetry, because I think for some of you, you work on higher point symmetry for a living, and for some others, it might be the first time you saw it, so it's hard to strike a balance. But let me just quickly say another example, the Chern-Simon theory. So now we're in one dimension lower, 1 plus 1D, 2 plus 1D, I'm sorry. Chern-Simon theory. This is at level k. So the theory is labeled by integer k. The Lagrangian k over 4 pi ADA. The technical comment that when k is odd, this theory can only be defined on spin 3 manifold. So let me not worry about it too much. So this theory is a little bit different from the one above. Maybe let me use capital A. It's written in terms of the same kind of gauge field. It's an ordinary gauge field. But the Lagrangian now has only one derivative in it, rather than two, as in the Maxwell case. And you have a lot of Wilson lines. That's the integral of A. And here n runs from 0, 1, all the way to k minus 1. When n is greater than that value, you can show that it's actually identified with the 1 in this range. Now the reason I want to bring up this theory is it's kind of even simpler than the one above. So up there, you see the one-point symmetries are continuous. We're in 3 plus 1D. The symmetry operators are exponentiation of these charges. And these charges are two-dimensional objects. And that's not surprising. In undergraduate electromagnetism, the Gauss surface is a two-dimensional object. And a two-dimensional surface can link with a one-dimensional line in 4 space-time dimensions. Okay, so that checks out. But you have two kinds of objects, right? You have the Gauss surface on the one hand. They generate symmetries. You have the Wilson lines on the other hand. They are acted by the symmetry. So you have the charge operator versus the charged objects. In 2 plus 1D Chern-Simons theory, you just have the Wilson lines. And they are both the symmetry operator and the charged object. So they act on themselves. So here you have a zk is discrete now, one-form global symmetry. Generated by Wn, and they act on themselves. So this picture now becomes accurate. And the fact that the symmetry operators are charged under themselves signals some kind of anomalies of the one-point symmetry, but I will not say too much about it. All right, that's all I want to say about higher point symmetry. If I continue, I think half of the audience will fall asleep. Any question up to this point? So now let's get back to this picture. It's weird to see myself. Okay. So now let's talk about non-invertible symmetries. So there are many different constructions of non-invertible symmetries in higher dimensions. Here I will talk about 2 constructions that I personally find very powerful. The first one will be called higher gauging. And the resulting non-invertible symmetry is sometimes known as the condensation effect. And the second one is called half gauging. Okay, how are they defined? I don't know if I should wait until that part of the blackboard to dry. Let's make it worse. All right. Let's see.
And you can use the thing there on the screen.
Isn't that even wider?
No, the other side.
Yeah, it's same thing.
Oh, the other side. You can see I'm a theorist. Thank you. All right. So before going into the details, let me say the raw idea for half gauging. The idea of half gauging is the following. So usually if you have a global symmetry, it could be an ordinary zero-form global symmetry, it could be a higher form global symmetry, you can gauge it. And sometimes there might be an obstruction and that would be a two-hoop anomaly. But assuming there's no anomaly, then you can gauge it. Gauging a global symmetry takes you from one quantum system to another. Sometimes the resulting theory might be isomorphic to itself, but generally you get a different quantum system. Higher gauging is the idea that you don't gauge the symmetry everywhere in your space-time. You only gauge it along a higher codimension. Let me draw it schematically as follows. So you pick say a codimension 1 manifold in your two-dimensional space, and you only gauge along this locus. Now, if you're far away from this locus, then nothing happens. You start with a quantum system, let's call it T. It has some global symmetry, Q-form symmetry. And you only gauge this symmetry along a codimension 1 manifold. So away from this codimension 1 manifold, you don't see any changes. But you generate some defect along that codimension 1 manifold. And that's known as higher gauging. The resulting defect is called a condensation defect. It's generally non-invertible. So this is the simplest case of simplest example of a non-invertible symmetries in general dimensions. Given any Q-form symmetry without anomaly, you can do higher gauging to construct a condensation defect. But you should really think about condensation defects as something extremely close to a very stupid or trivial non-invertible symmetry. It's almost like a projection. It's like a categorical version of a projection. I'll say more about that in just a minute. A more non-trivial example can be found using half gauging. So in half gauging, we start with the system T. It also has a higher form symmetry G. Now instead of gauging it along a higher codimensional manifold, you now gauge it in half of the space-time. So you pick a codimension 1 cut, let's say x equals to 0. And on one side of the cut, you gauge the symmetry. You might be wondering, what does it even mean to gauge the symmetry on only half of the space-time? I'll try to make that precise in maybe the next lecture. So on one side, you get a different quantum system, P modeled by G. Now generally, this gives you an interface between two different systems. It could be Ising model in the low temperature phase on the one side and Ising model on the high temperature phase on the other. So let me call this interface D. The idea is that sometimes it could be that the system before gauging and after gauging end up being isomorphic. And in that case, you can just remove the shaded region because they're isomorphic. To be more precise, you have to put another isomorphism interface. Then D becomes a defect in a single system, and that's generally non-invertible. This is extremely abstract. I didn't provide you any details. You're only supposed to understand it at the level of the picture. But already from the picture, you can derive some interesting fusion rule. So let's say you have the interface from half gauging. That means on this side, the theory is T now T. And on this side, you have T. But then I can compose this. I can set up the orientation reversal interface on the right. And that's just doing the G gauging instead of to the right, but to the left. If you compose D with its orientation reversal, now you are only gauging in this intermediate region. Later on, I will explain why these two objects are both topological, meaning that you can bring them close to each other. And when you bring them very close to each other, you are effectively gauging a very thin interval in between. And that in the limit becomes gauging only along a higher codimensional manifold. So just from the picture, you find the fusion rule that D times D bar is C. And that turns out to be quite a universal fusion rule for many of the non-invertible symmetries. In fact, we already saw such an example yesterday. Yesterday, in Ising, we found a fusion rule, B times D is 1 plus eta in the continuum. On the lattice, there's a lattice translation. There's some factor of 2. Don't worry about that. When you go to the continuum, this is the algebra. And if you identify C with 1 plus eta, this is exactly the same fusion rule.
I'm not sure I understand this. So what is C given D? Like how do I compute, or C is just by defined to be D bar?
C is defined as gauging along a higher codimensional manifold. D is defined as an interface by gauging half of the space-time. So these are two different bullet points, and from the way they are defined pictorially, you can see that they obey this fusion.
Could you explain why in the self-dual case, this implies that D is non-invertible?
Oh, well, I didn't really explain that yet. Right, so in the self-dual case, the red region is, you can erase the red by applying an isomorphism, because T mod G is basically the same as T. Now, the statement is, so one thing you notice is that D times D bar is not 1. It's something non-trivial on the right-hand side. If it were invertible, you would expect D times D bar literally being 1. Of course, at this point, you can question, given D, how do I know the inverse element, if it exists, has to be D bar? Maybe it could be something else. How do I show that there isn't an inverse such that D times D inverse is literally 1? And I couldn't at this point. But later on, when I talk about how they actually act on the state, you can usually find an explicit kernel. And that would prove that it's really non-invertible. There could be some funny cases where C ends up being the identity operator. Then it is not. It is invertible. All I was saying is that generally it's non-invertible, and we'll do examples later on.
Could you raise the lower board just a little bit, so that they can see the screen?
Raise it?
No, just raise it a little bit.
Lift it up.
Lift it up.
Okay, I'm doing
just
that.
A bit further.
Okay.
Thank you.
Oh. Sorry. Okay. Yeah, this is an important equation. Maybe I should have written it.
No, you can lower it again. It's fine.
D times D bar equals C.
Can I ask another question?
Yeah.
In this half gauging case, in the case that T and T gauged are isomorphic, aren't we back in the first case, in the condensation case? Because now D would go from T to T third, right?
Okay, that's a good question.
Or is it like?
But the answer is no. They're different. Yeah. So just seeing the picture. So if you just have T and T on both sides, you can have many kinds of defects in between. When T mod G happens to be isomorphic to D, this is a different defect compared to C in general. In fact, their fusion algebra tells you that they're quite different. In that case, both T and C are defects in a single system P, so they are different defects. Example, for instance, if T has an ordinary U1 global symmetry, you can take a defect that rotates that implements the U1 rotation by pi over 4. You can have another defect that implements the U1 rotation by pi over 7. Both of them are defects in a single quantum system, but they are different defects, just like C and D in that case. Yeah.
So in the picture of like the D and D bar, no, you did like the right gauging, let's say, with the bar, no, the rotation reversal. But actually you have like also like the quantum symmetry in T mod G, no?
Oh, that's a good question. Yeah, that's something I will address in the next lecture.
Okay, but they're not the same thing.
Generally, they are not. When they are isomorphic, one information I have to specify is that the quantum symmetry is dual.
Yeah.
Is identified with the original one. And that restrict the form degree Q over there. Yeah.
So if you have like a general symmetry group G, then is C always of the form like one plus every defect for every element of the group?
You're asking me what does C look like generally? Yeah, maybe that's what I can explain the remaining 5 minutes. Because I want to wrap up the higher gauging discussion this lecture, and next lecture we'll talk about half gauging. Yeah, so let me just quickly say what it looks like. Okay. So half gauging. Sorry, higher gauging. Okay, I'll be very brief. You can look up more details in my TOSI lectures. The simplest example will be 2 plus 1. Well, first let me make a quick comment. Higher gaugings are trivial for ordinary zero-form global symmetry. It's because ordinary zero-form global symmetries are codimension 1 in space-time. So if you want to gauge it only on a codimension 1 manifold, it's too crowded, right? You just put this zero-form global symmetry here. So higher gauging for ordinary zero-form global symmetry is just taking superposition of the defect. Let me just write it in words. So higher gauging for zero-form ordinary global symmetry. Whenever you see 0, that means you can turn off your brain. That's the ordinary one. For zero-form symmetry, you're just adding, literally adding the defect. Okay. This is codimension 1. You are doing your higher gauging on a codimension 1 manifold. There isn't too much room for you to play with. You're just adding it up. And this operator has a name. This is proportional to the projection operator. All right, so far we haven't done much. And that's actually the reason why in the Ising case, okay, some people cannot see here, in the Ising case we have eta, the Z2 symmetry. 1 plus eta is the most stupid kind of condensation defect from higher gauging. So to have an interesting higher gauging outcome, you have to talk about higher form symmetry. But it's not the ordinary gauging of the higher form symmetry. It's gauging it only on a higher codimensional manifold. I know this might be jumping a few steps ahead for some of you who are not familiar with higher form symmetries because you haven't even thought about how to gauge the higher form symmetry in an ordinary way, and I'm forcing you to talk about gauging higher form symmetry in a higher way. But let me just answer the question earlier. So the simplest setup to demonstrate higher gauging is to have a 1 form symmetry. And you can do it in 1 plus 1D. It's a little bit too crowded because you have degenerate vacuum. So it's even cleaner to do it in 2 plus 1. And that's why I keep that part of the blackboard. In 2 plus 1, a 1 form symmetry operator is a line, like the Wilson line up here. I remember, so a Q form symmetry is generated by something of codimension Q plus 1. Q is 1 here, so it's codimension 2. In 2 plus 1, codimension 2 means that they are lines. So what does it mean to gauge a 1 form symmetry only on a codimension 1 manifold? Codimension 1 in 2 plus 1 is the surface. That means this defect C, this condensation defect, should be viewed as a network of the 1 form symmetry line. And I can write it slightly more precisely in the equation, and that will be the last equation I wrote in this lecture. So let's say this surface is sigma. And let's say this line is eta. So eta is the line here. It depends on, it's supported on a one-dimensional manifold. And that I denote by gamma. So this picture is trying to say that this surface defect, even though I say it's a surface, so I try to draw, try to shade this region to make it a surface defect, it's actually secretly a mesh of lines. And the precise meaning is that you are taking a sum of line operators, and you are taking the sum over the non-trivial 1 cycles on this 2 manifold where you try to define your condensation defects. These are homology class with coefficient in G, where G is the 1 form symmetry group. It could be Zn for simplicity. There's some normalization, don't worry about it too much. But that's the basic idea. It's a surface made out of lines. And you see, this in spirit is very similar to the projection operator. But in projection operator, you are adding objects of the same dimensionality. You're just adding a bunch of surfaces together. And therefore, projection operator is not simple. It's very derivative. It's made out of other, it's a linear combinations of other defects of the same dimensionality. But that's slightly different from condensation defect. Condensation defects cannot be written in terms of the sum of other surfaces. Rather, it's the sum of other lines. So it's something in between a projection operator versus a genuine surface operator. So it's in many ways the most trivial or elementary example of a non-invertible symmetry. Okay, I'll stop here. Oh, sorry.
Yes,
Maybe I'll first answer the question.
Here, if you have more than one topological line in 2 plus 1D, say the Wilson line of n equals to 1 and n equals to 7, whatever, does the choice of eta make a difference? Or?
Yeah. So here, you see, I'm summing over the homology class with coefficient in G. So, it's not just summing over one species of line, right? You're actually kind of summing over eta, eta squared, eta cubed, etc. So the name of the game is that you pick a one-form symmetry group. So this corresponds to a set of lines that are closed under multiplication, under fusion, and you condense them in this particular way. The question that you can ask is, can you do that? Is there an obstruction in doing that? Is there a consistent way to do that? Generally, there isn't a consistent way, and that signals some kind of anomaly. So it's a higher anomaly. The second question you can ask is that given a set of lines, is there a unique way to do it? And the answer is also no. There are generally multiple ways to do it. That corresponds to some higher notion of the discrete torsion. Any other questions?
Is G required to be abelian?
So that's one thing I forgot to say. For higher form symmetries, when it's invertible, the symmetry group is always abelian. It's because when you try to fuse them, you can do it this direction or you can do it this direction. There's ambient space where you can change the order of the product. For zero form symmetry, you cannot move it around. For higher form symmetry, you could. So the algebra is always commutative. It's always abelian. This normalization. Well, I didn't say arbitrary. I say you don't worry about it. It's not arbitrary. It's fixed by the gauging procedure. Yes. It's not arbitrary. That's some of the most painful parts of writing those papers. To figure out exactly what the normalization is. Any other questions? Yes.
Sorry, I'm a little bit confused. What kind of thing is that? Are you summing like the eta?
Oh, I'm sorry. Maybe I'm writing too small. I'm summing over gammas. Gammas are in H lower one of the two surface with coefficient G, where G is a finite abelian group.
Yeah. So what is eta doing?
Eta is the symmetry operator for the one-form symmetry. It's an operator. So for instance, it could be the Wilson line over here. So this formula, the way you should read it, is that this eta is some one-form symmetry operator, it's some line operator. And that's given as input, and I'm giving you an output, which is a surface operator. It's like a machinery where you can take a one-form line operator, and you get a surface operator.
Sorry, I might still be a few steps behind. When you say like a line operator, this is like a space or?
Not necessarily, it could be. So by a line operator, I mean, for instance, in gauge theory, you can consider the integral of your connection along a line, and that will give you a line operator. You can view it as an operator acting on the Hilbert space. Alternatively, you can orient it in the time direction. That would be a defect modifies the Hilbert space. So it's again the same principle we talked about yesterday. Every symmetry should serve as both as a conserved operator or as a defect that changes the Hilbert space.
Is it known for which theories or surface defects are of this form?
That's a good question. You can do something even better than that. I don't even have to tell you what the theory is, because all that goes into the computation is what this one-form symmetry is. So if I tell you what the input one-form symmetry is, together with its anomaly, that's very important, then I can tell you the fusion algebra of C. Maybe I'll do one example in the next lecture, since many people are interested in what this object is. Sometimes I try to skip the condensation defect, because it ends up being the trivial thing. In many papers, people are trying to model by the condensation defects. But it's really fun to work with them. It's always important to understand the most trivial object. Any other questions?
One thing that I didn't understand about this construction, there's sort of three numbers here. It's three input numbers. You have the p-form symmetry, you have the dimension of the defect, and you have the dimension of space-time. Is there a relation? Can I only...
Excellent question. Yes, there are three numbers. Yes, excellent question. Here, D is 3, Q is 1, and I pick a codimension 1 manifold. And you are absolutely right. A priori, these are three independent numbers. But there is a relation. And the relation is the following. The relation is that, so if you try to P-gauge the Q-form symmetry, by P-gauge, I mean to gauge it in a co-dimension P manifold. Again, when P is 0, that's the ordinary thing. So there are really two numbers, you are right, and there's also one other number denoting the dimensions. When you try to P-gauge a Q-form symmetry, you don't want the dimensions of the defect or of the higher form symmetry to be too big. If it's too big, it doesn't make sense to gauge it in that higher codimension manifold. So you want Q plus 1 to be greater or equals to P. Because this guy is codimension P minus Q minus, sorry, codimension Q plus 1. This guy is codimension Q plus 1. You're trying to gauge it on a codimension P manifold. So the dimension of this, the locus has to be greater than that, and that means the codimension has to go in the other direction. And when the equality is saturated, then it just corresponds to a projection. So it's only interesting when it's a strict inequality. So this is the and you can see that to get when P is 0, that's the ordinary gauging. So to get P equals, so if P is 1, you at least need Q equals 1. So that's why I picked this as the simplest possible example of that. So maybe we should take a 5 minutes break. I'm sorry I went over time. I stopped on time, but then there were many interesting questions. So. So let me say a little bit more about this condensation method. Okay. So let me just, I won't give too much details, but let me just sketch the simplest possible example of the higher form symmetry. Not a higher form symmetry, the condensation defect. So as I said, the simplest case would be working 2 plus 1D and do one gauging, meaning that you're gauging a codimension manifold. And let's gauge Z2 1-point symmetry, so Q is 1. And I encourage you to check that when P and Q are both 1, this inequality is satisfied. And you gauge such a symmetry to get a surface defect. All right. Now, but to describe that, I have to say a little bit about a Z2 1-point symmetry in 2 plus 1. To be more precise, I'm working with bosonic quantum field theory. So I don't want to choose a spin structure. Now it turns out that there are 4 options for the Z2 1-point symmetry. On the last term, this is described by a graded fusion category. And if you are familiar with that language, there's an R symbols. There's also an F symbol. And the R symbol is characterized by the topological spin for abelian manual. Theta. Now for Z2 1-point symmetry, there are exactly 4 possibilities. What's my convention for theta? I think theta is identified with theta plus 1. So for Z2 1-point symmetry, there are 4 possibilities. Theta can be 0, a quarter, a half, 3/2. So I'm not explaining where this comes from. You just have to take my word for it. And in condensed matter physics, they have names. This is known as a boson. The theta measures the spin of, well, let me write down the definition. So theta is defined as follows. You have this line, Wilson line operators. And let's say you have such a configuration. And as you unbraid them, to fix these two edges, you just do some local move from here. Our move, and then you face. Wait, for my definition, okay, let's see. Theta is 1, I minus 1 minus not by exponentiation. Okay? Now, when there's no phase, that means it's a boson. Right, so what is this picture doing? This is literally the definition of statistics. You have two identical particles, right, and you exchange them, and you compare that with the configuration where you just let them propagate. If you get a phase, then it's not a boson. If there's no phase, it's a boson. If there's a -1, that's the fermion. If you have something in between, in this case, it's called a semion. More generally, it's a semion. This is the anti-semion. Now, there's F symbols, which tells you the relation between this and this. So these are two different moves you can do on a Z2 one-point symmetry. Now, in this case, the F symbols turns out to be the square of the R symbol. This is something you can easily show by playing with pictures. Okay, this R symbol generally signals an anomaly for gauging the one-point symmetry in the entire space. It's an ordinary anomaly for one-point symmetry. The idea is that you cannot condense something that's not a boson. But here we're not doing that. We're less ambitious. We're not gauging the one-point symmetry in the entire space-time. We're only gauging it. We're only picking a codimension 1 surface and try to gauge our one-point symmetry over there. If you're on a two-dimensional space-time, this picture doesn't make sense, right? Because when you try to do the statistics, you need a three-dimensional space-time. So you don't care about this when you are just trying to do one gauging. But you do care about this. This picture does make sense on a two-dimensional space-time. And that signals the obstruction. So you don't care the value of theta. You only care about the value of theta squared for one gauging. So this is known as the one anomaly. I'm being very fast, I'm sorry. So the upshot I want to say is that if you want to one gauge the one-point symmetry, you can only do it for boson and fermion. You cannot do it for semion and anti-semion. And it's a very interesting algebra to show that the resulting condensation defects are the following. So you have these two cases. This is the boson case. This is the fermion case. In the fermion case, the resulting condensation defect is a Z2's ordinary symmetry. So I'll put a 0 here to denote that it's an ordinary zero-point global symmetry. In the case of a boson, you get a more interesting non-invertible algebra. Where sigma is the support of this surface. And this you can view as the partition function of the 1 + 1 dz2 gauge theory. You might as well write it as this. Okay. All right, I think that's all I want to say about condensation defects. I don't want to say too much, but the upshot is that this is the simplest example where the input is a one-form global symmetry. You can only one gauge it when it's a boson or a fermion. When it's a fermion, you get something much easier. The output is a Z2 zero-form symmetry. In fact, this is the charge conjugation symmetry in Chern-Simons theory, if you have ever studied Chern-Simons theory. In the case when it's a boson, it's non-invertible. this algebra is not group-like. In fact, the fusion coefficient is like a TQFT.
All right. So when you said bosonic over there, you meant that the symmetry is bosonic. Or
Sorry, by bosonic I mean this the TQFT here, not TQFT. The quantum field theory here does not require a choice of the spin structure. Okay. It's either the frame or the oriented case.
What do you mean with the statement that these are artificial functions or QFT two-dimensional?
Yes.
What do you mean? What do you mean by this statement?
That is bosonic.
No. The number is artificial function. What does it mean in practice?
Well, in practice, it means that you insert two parallel C. Then it's equivalent to the right-hand side with the insertion of only one surface, but multiply by the TQFT partition function of the C2 gauge theory. It's the equality at the level of the
So is it not like the TQFT is leaving this?
You can think about it that way. So you start with two parallel C's.
Yeah.
You fuse them,
Yeah.
then it equals to a decoupled TQFT living on the
leaving
D.
on the.
That's right. That's right. So it's 1 plus 1D, right? It's
Yeah,
a 1 plus 1.
that's one.
That's right. I can give another lecture about why the coefficient should be TQFT, but maybe I should move on. But any more question about condensation defect before we move on? All right. Now we go to half. All right, so we start with a quantum system T in B space-time dimension. And I assume it has a Zn2 constant. You can consider more general finite Wheeling group, but let me do Zn for simplicity. Most of the examples we'll do later on consists of only one Zn. And I'm going to assume that it has no anomaly. No anomaly in the usual sense that it can go through the entire space. Now, because there's no anomaly, I can talk about the theory where Zn is gauged. One comment is that given an anomaly-free global symmetry Zn, there are generally multiple ways to gauge the symmetries. Here I'm not specifying which way I'm gauging it, but it does matter. So I'm just loosely denoted as T mod Zn. So what does that actually mean? It means that at the level of the Lagrangian, the T mod Zn Lagrangian is the Lagrangian of T coupled to the gauge field of the Q-form symmetry. So remember, for ordinary symmetry, you have for ordinary zero-form symmetry, the gauge field is a one form. For Q-form symmetry, the gauge field will be a Q plus one form. Just because, as we discussed in the previous lecture, the current has Q plus one legs. So to contract it with the gauge field, you have to live with the Q plus one form gauge field. To make it a Zn gauge theory, you add to it a B of action. So that's the Lagrangian for the T mod Zn. A is a Q plus 1 form gauge field, B is a D minus Q minus 2 form gauge field. So this thing is called BF term. dA is F, this is B. There's a coefficient N, it's the same N over here. And I probably won't be able to review too much about BF theory from the field theory point of view. But the intuitive way to think about it is that if you integrate out B, you should think about B as a Lagrange multiplier. Meaning that if you integrate it out, it forces A to be a Zn value gauge field. Without this term, A and B a priori are just U1 gauge field. But we're doing discrete gauging, so we want to restrict the holonomics.
The coupling to the initial theory is like minimal coupling to
Oh, this one?
Yeah.
Well, it depends on what you mean by minimal coupling. So that's part of the ambiguity in saying that I can gauge it. I generally do allow more options, but here I'm hiding the choice in L of. Could be minimal coupling, could be something else. Okay. Now, why do I write down this form of gauging? The reason I need this is because T mod Zn, T has a symmetry, a global symmetry Zn. After you gauge it, it has a quantum symmetry, or dual symmetry, or orbital symmetry. We briefly talked about that yesterday in the Ising model. But it's more generally true in higher dimensions. T mod Zn has a Zn hat symmetry, which you can think about wrap of Zn, which is isomorphic to Zn. But its form degree is D minus Q minus 2. And that's quite complicated. Even I cannot remember this linear combination all the time. And let's see where it comes from. Well, let's first do some sanity check. When Q is 0, that's an ordinary symmetry. And when D is 2, that's the case we discussed yesterday in the Ising model. 2 minus 0 minus 2 is 0. So for a zero-form ordinary symmetry in two space-time dimension, when you gauge a Zn, you get a Zn ordinary symmetry back. That was known in the physics literature back in the 80s by Komra, Vafa. Now, there's a generalization of that fact to higher dimensions, and that's what I want to explain over here. In this gauge theory, we have the gauge field little a. And therefore, I can write down a Wilson line for that little a. And I can write it as eta. So I can pick a closed Q plus 1 cycle and integrate my little a gauge field along that Q plus 1 dimensional manifold. Now, one nice fact about this eta is that it's topological. The reason it's topological is because the equation of motion for B tells you that it's a flat connection. This is not true for the Wilson line of B. Because the equation of motion for A is more complicated. It's coupled to the complicated quantum system T. But the equation of motion of B is linear. To integrate it out, it tells you dA is flat. And therefore, the Wilson line of A is topological. So the way I wrote this equation is that I start with T, I couple it to some BF theory. The coupling is hidden here. But there's an alternative way to view it. I can start with the BF theory, which is a topological on the field theory. And if I just have BF theory, I have the topological Wilson line of Wilson operator of A, I have the Wilson operator of B. Both are topological. B and A are on the same footing, if you just look at this part. But then you introduce some non-topological degrees of freedom from T, and it talks to A. So it breaks the topological nature of the Wilson operator for B. But you can think about it as electric matter. It's like in Maxwell theory, if you introduce electron, it modifies the D star F equation. But it preserves dF equals 0. To add something to the right of this equation, you add electron. To add something to the right of this equation, you add monopoles. This is what we are doing here. You add some electrically charged particle, and that break half of the symmetry, but you preserve the other half. And that would be very important later on. So the upshot is that we can consider Wilson operators of A. They are topological because of the equation of motion for B. Every time you have the topological operators in this modern language of thinking about generalized symmetry, that gives you a higher form symmetry. Now we just have to count the degree. Now if you believe me, that's the degree over here. Now, for instance, when Q is 0, that's a line, and that corresponds to minus Q. Okay, if it's the first time you have learned higher form symmetry, you probably cannot do the subtraction in real time. But if you take the, if you look at the notes from the previous lecture, you'll see that this is the correct. But anyway, the upshot is that there is a dual symmetry. Z hat, and it's generated by eta, the Wilson operators. Oh, yes, because the Wilson operators are labeled by representations of the gauge group. Yeah. Yeah. That's right. Yeah. Rep G is just a fancy way of saying Wilson lines for physicists. Yeah. Any other questions at this point? Great. Now we're going to talk about this interface. To talk about the interface, let's first look at the BF theory on its own. So I just have to if you just have the BF theory, there are two kinds of boundary conditions you can consider. I'll soon connect to the interface, but let me first talk about boundary condition. In fact, we briefly talked about it during the discussion session with David yesterday. The first boundary condition you can talk about is the Dirichlet boundary condition, where you just set the restriction of the gauge field to the boundary. This vertical line means the restriction of the form to the boundary to be 0. Now there's a question about which one you call Dirichlet, which one you call Neumann, because A and B are really on the same footing. So here I kind of make a choice. I view it as a gauge theory of A, and therefore this should be called Dirichlet. But you can switch your opinion and call this one Neumann. But for us, it's more natural to call this one Dirichlet because eventually we're going to couple the non-topological quantum field theory to the BF action via the K equation. On this side of the blackboard, it's just a matter of convention. This is a topological boundary condition, meaning that if you have the boundary here, and you set A to be 0, in any Euclidean correlation function, and you can intuitively understand it from the equation of motion from B. And this is the Dirichlet boundary condition that was discussed yesterday. Alternatively, there's a Neumann boundary condition. For Neumann boundary condition, usually when we talk about it in physics, we mean that the derivative of the field vanishes on the boundary. And Dirichlet means that the field itself vanishes. So this terminology makes perfect sense. But here you are tempted to write something like dA vanishes along the boundary. That's what Neumann is for in ordinary quantum field. But dA is automatically vanished because of the equation of motion for B. In fact, the right way to think about the Neumann boundary condition is not in terms of the derivative of the field, but you should work in phase space. In phase space, you have the coordinate, you have the conjugate momentum. The originally boundary condition is setting the coordinate variables to be 0. Neumann boundary condition is setting the conjugate momentum to be 0. For Maxwell theory, the conjugate momentum of the gauge field is the field stress. That's the derivative of A. But here we're not doing Maxwell theory. We're doing some BF or Chern-Simons-like theory. The conjugate momentum of A is B. So the Neumann boundary condition is setting B to be 0. Okay, so these are two topological boundary conditions. I'm not saying that these are the only two, but these are two topological boundary conditions.
Just one thing about other ones. So when A and B are of the same degree, another natural thing you could do is choose some linear combination and set that to 0.
That is true. Yeah. So well, there is some subtlety to that. So for instance, let's take B to be 3, Q to be 0. So both B and A are 1 form. Right. Good. That theory has that theory is the Z2 gauge theory in 2 plus 1D. If you talk to a condensed matter physicist, he or she will refer to it as a toric code. A will be the E anion, B will be the M anion. Now you can ask, can I set A plus B to be 0? Good. And the answer is that you couldn't quite do that, in the sense that it won't give you a topological boundary condition. And that's because of an anomaly. So it's more subtle than the analysis we did. And there's a very nice paper in the field theory context by Anton Kapustin and Solina. They classify when you can set some linear combination of the gauge fields to be 0 to obtain a topological boundary condition. And yeah, Konstantin and Dan Fried also has a nice, relatively recent paper doing this from more TQFT point of view. Yeah, that's a very nice. But here, for our purposes, I'm only going to talk about these two boundary conditions. In fact, I'm only going to talk about this. Any other question at this point? So now we are ready to do half gauging. So to do half gauging, the first question you should ask is, what does it mean to gauge in half of the space-time? So on the left, I have my quantum system T, I have a Zn Q-form global symmetries. And now I'm just drawing a line in my space-time. So far there's no physics, I just draw a line up superficially. And then on the right side, I gauge the symmetry. So deep on the right, I know my Lagrangian is just given by this. So on the right, I have some new fields A, I have some new fields B. Deep on the left, I don't have A and B, it's just the original system T. Now the question is, what do I do in the middle? In the middle, I set my A to be 0, using this boundary condition. So I'm imposing a Dirichlet boundary condition on the new dynamical gauge fields A and B that I introduced only on the right. And I impose a boundary condition for my gauge field. This is a consistent configuration. It's not only consistent, it's also topological. The BF theory has these two topological boundary conditions, but the moment we couple it to T, one of them remains topological, the other is broken. This one is the one that remains topological. By the same argument, why that Wilson line is topological, Wilson operator. So this actually gives you a topological boundary. This is a topological boundary for the gauge field, but now it becomes a topological interface between two different quantum systems, T and T mod Zn. So my terminology is that when I say an interface, it's an interface between generally two different quantum systems. When I say a defect, it's a defect in a single quantum system. So far, it's an interface. So I'm going to call this interface D. Now on the right, as we discussed over there, there's a quantum symmetry. Z n hat D minus Q. I cannot remember it. Q. So that's something you can always do. It just depends on the fact that T has a non-anomalous Z and Q form symmetry. So we haven't got to any non-invertible symmetry yet. To obtain a non-invertible symmetry, it only applies to some special systems. And I'm going to specify the condition that needs to be satisfied. So this is one important difference between higher gauging and half gauging. In higher gauging, the moment you have that Q-form symmetry, you can just gauge it on a higher codimensional manifold, assuming there's no anomaly. So it's completely universal. Every time you have a higher form symmetry, you can consider those higher gauging and condensation defect. For half gauging, every time you have such a non-anomalous higher form symmetry, you can do half gauging. You get an interface, but not a defect yet, not a symmetry yet. A symmetry has to be something that maps the original system back to itself. So now I'm going to write a big if. And only when this if is satisfied, we will have a non-invertible symmetry. And this big if is that the T somehow happens to be isomorphic to its gauge version. It doesn't happen every day, but it happens for some special system. And I will give examples of when this is the case. Yeah?
Does that symmetry also have to match?
Good. I'm about to write it. So the symmetry Zn is also required to be the same.
So they already give a dimensional constraint.
Yes, that's also the next thing I'm going to write. So then this equality only makes sense if Q equals D minus Q minus 2, and that means Q is D minus 2 over 2. There was another question, yeah?
Yeah, are we asking for these to be isomorphic on the nose or just equivalent?
Isomorphic, yes. And in physicist terms, that means I allow possible counter terms in the isomorphism. Namely, if you compute the partition on both sides, they might not be literally equal as numbers on the nose, but as long as there are equivalents up to counter terms, then that's good enough.
Ask about what happens if you try to do the same thing with the Neumann boundary condition.
Then
you
it's
said
not
it's no longer topological, but do you still get a non-topological interface?
You do. Now, there's nothing wrong with that. But it flows under renormalization group flow, and it's more complicated. It's not going to, generally it won't lead you to a symmetry, but it's a configuration you can consider, definitely. But the goal of this talk is to find and identify a symmetry, which has to be topological by assumption. Any other questions?
Yes. In this equivalence, it's not just a Lagrange equivalent, right? All the symmetries have to be the same. Like for instance, in the Majorana case and the Ising, one could not say that those two are equivalent.
They are not. Okay. They are not equivalent. Yes. Okay. So from this equation in particular, it only makes sense when D is even. Quick observation. But in odd space-time dimension, there are some slight variation of the construction you can do. You just cannot start with a single Q form symmetry. You have to start with a Q1 form symmetry times a Q2 form symmetry. And then you can play similar game. But let me not. So when this is the case, then you have T here, you have T mod Zn here, which is isomorphic to T, and therefore you get a defect. And the claim is that this is generally non-invertible. And this is the half gauging construction. All right, this is pretty abstract, but it's also very general. Many of the non-invertible symmetry in general dimensions can be constructed this way. And I'm going to go through various examples in the remaining of this lecture. Actually, before that, I have one more thing to say. How is this? Here we pick this boundary condition. Okay. Now, let me talk about some algebra. Let me emphasize that for the following algebra, we don't need the big if. So it's true regardless if that if is satisfied or not. So the first algebra we already talked about last lecture. Oh, I lost my red chalk. Where's my red chalk? The first algebra is that d times d bar is C. There's a second one that's kind of interesting. You can ask, what is d times? Write it like this. So you have t here, you have d here, and if you have another color here, you can have eta here. Remember, eta is the exponentiation of integral of a. Okay. So what you find is that d times eta is what? Okay, so eta is defined here. So at the interface, it's defined as a topological boundary condition where a vanishes, right? So when you put eta to the interface, it trivializes by definition. So d times eta is d. And if you recall, that's one of the relation we found in the Ising model yesterday. But now it's made manifest by construction. Okay? All right. And these are the two main algebra we have. D times d bar is C, the condensation defect. D times eta is D. There's also eta times D, but eta now has to be interpreted as differently. It's now dual symmetry when you view T as the gauge theory of T mod Z. As we discussed yesterday, gauging is invertible. It's reversible. So you can view this side as the gauge theory of that, or conversely, you can view this side as the gauge theory of this. All right. So to make it more concrete, let's do examples, and hopefully this algebra will come to life.
Next question, you raise the board?
Yeah.
Can be the if, maybe it's like, if the theory is like the gauge theory and the other theory are not like directly isomorphic, or they are like S2 or whatever.
Oh yeah.
Is it a generalization of that?
So by isomorphism, I don't mean some particular Lagrangian description. I mean as if the underlying quantum field theories are isomorphic.
Okay.
So generally, I will need to use duality in that isomorphism, and that's going to be the case in the examples I'm going to cover right now.
No, because I was thinking about the circular point of Ising.
Oh yeah, well that's the example. You're getting ahead of me. So that's the first example, indeed. So let's try to recover the non-invertible symmetry in Ising that we discussed yesterday. From this perspective, Yesterday, we started from the Majorana fermion, and we do bosonization to get a non-invertible symmetry. But now we have a different way to look at it. Okay, so D is 2, Q is 0, N is 2. This is just an ordinary Z2 global symmetry. In this case, the condensation defect is trivial. Now the condensation defect is a line, so we are at 0, we are 1 gauging a 0-point symmetry, and it's just 1 plus eta. And you can take my words for it, but in equals to 2, the non-inverted interface the defect is the same as d bar. Maybe this is too quick. Let me get back to this point. Because at this point, this makes sense. Okay. So you can take icing at the critical point. So it's very important we are at the critical point, the CFT. The statement is that icing is isomorphic to icing mod Z2. And that's nothing but the Kramer's linear duality. Is everyone familiar with this isomorphism, this duality? So let's say a little bit more. I don't know how much I should say. So there are different ways to say it. Icing CFT is the simplest conformal field theory in 1 plus 1D. And there's a classification of conformal field theory in 1 plus 1D. If you look at the classification list, there's only one CFT of that central charge. Central charge is some measure of the degrees of freedom. A does not change any central charge. So icing mod Z2 has to be a CFT of the same central charge, but by the general classification, there's only one such CFT, so they have to be isomorphic. That's the field theory way of arguing it. It's not the physical way to argue it. The physical way to argue it is that if you go away from the critical point, gauging the Z2 in the icing model, flip the temperature. It takes you from the high temperature phase to the low temperature phase. So it's generally not a duality. But if you tune the temperature to be the critical temperature, then gauging leaves it invariant. And that's the statement over here. Okay, I probably cannot do any better. I mean, Kramer's one-year duality in icing model is a subject on its own, so I probably just have to assume it from here. All right. Okay, so this is one case where the if is satisfied. And the Z2 of the original icing is identified with the quantum. And you have to take my word for it, but when D is 2, D equals D. It's not a very deep fact. It has to do with some minus sign coming from the form degree of the gauge field, but it's true. So then let's copy the general algebra we obtained here. So D minus D is C, and C is just 1 plus eta. D times eta, eta times D is D. And that's exactly the non-invertible algebra we found yesterday from the lattice. Well, I have to take a continuum limit, but that's going to be. That's one example. Let me do another example. So example number 2 is the 3 plus 1D U1 gauge field. U1 Maxwell field. The Lagrangian is minus 1 over 4E squared, F mu nu, F mu nu. as we discussed, there's a U1 electric one-form symmetry. There's also a U1 magnetic one-form symmetry, but I'm not going to use that. The name of the game here is that we pick a discrete finite symmetry and engage it. Oh, actually, there's one thing I want to say here. I'm sorry I forgot. In the Ising case, there's one very important thing, which is using the half-gauging construction. It makes manifest how the non-invertible symmetry acts on the operators. Let's say you have D here, and you take a local operator here, that's Z2 odd. The Ising conformal field here has a Z2 global symmetry, so it has odd and even operators. One of the most famous odd operators is known as sigma. That's the older operator. Ising is the simplest example of a Landau phase transition. In Landau phase transition, you have Z2 symmetry breaking phase and Z2 symmetry constructing phase. And sigma is the older parameter. It's a local operator, or you might also call it a point operator. Now you can ask what happens when you bring this topological line, the non-invertible symmetry, past this older local operator. The topological defect D is constructed by gauging in half of the space-time. So as the line goes past through the sigma operator, sigma experiences the gauging. What happens when you gauge a global, what happens to a local operator that's charged under a global symmetry when you gauge that very symmetry? Let's do one simple example that should be familiar to people who have taken quantum field theory classes. Start with a free fermion, free Dirac fermion in 3+1D. It's a local operator, the Dirac fermion. When you gauge the U1 global symmetry, by definition, the Dirac field is no longer gauging variable. The proper way to think about it is that it's attached to a Wilson line. Right? Ken Wilson's one of his most important contributions to physics is the introduction of the Wilson line. And Wilson line is a way to make a gauge non-invariant local operator invariant, but at the price of attaching it to a line. And that's what's going to happen to the sigma operator. As it goes to the other side of D, it experiences that gauging. And as a result, it's no longer a local operator, but it's attached to a Z2 Wilson line. Eta is the Z2 Wilson line. And that's the generator for the Compton Z2 symmetry. And this is the hallmark of the non-invertible symmetry. In this Euclidean process, you see that it takes a local operator to something that's not quite local. Rather, it's attached to a line defect. Ordinary symmetry maps a local operator to a local operator. If you have a U1 rotation symmetry, it maps a complex scalar field phi to e to the I pi over 7 times the same scalar field phi. But for non-invertible symmetry in this Euclidean process, it generally maps a local operator to something non-local. And this figure we will see again in my last lecture when we talk about QED. Another way another concept, I should say that this operator mu is known as the disorder operator. So the non-invertible symmetry in the Ising conformal field theory exchanges order with disorder. And that's the hallmark of the Kramers-Wenier duality. Kramers-Wenier duality exchanges order with disorder. I'm sorry that it might not make too much sense to some of the mathematicians friends here. But yeah, I probably don't have time to say too much about Ising model and Kramers-Wenier duality. But just remember this picture, it will come back again. What else do I want to say? I think that's it. All right. Okay, so any question at this point? Yes.
Is there an easy way to say why it's called order and disorder?
What do you mean exactly? Do you want me to explain the terminology order and disorder? Or
Yeah, physics.
Oh, in physics. So order means the following. So in physics, you might have some global symmetry in your quantum systems. In this particular case, it's just a bunch of spins. So it can be spin up or spin down. And the Z2 symmetry flip all the spin at the same time. Now, order parameter is an operator. Okay, so take a step back. If you have a global symmetry Z2, for instance, you can ask whether that symmetry is spontaneously broken or not in your vacuum. So the vacuum is a particular state in your Hilbert space. It's the lowest energy state. If vacuum can be degenerate, you can have multiple states of the same lowest energy. So the question is, how does the global symmetry, in this case Z2, act on your vacuum manifold, on the vacuum state? You have a non-degenerate ground state where Z2 leave it invariant. In that case, the Z2 is not broken. But you could also have a case where you have multiple ground states in infinite volume, and the Z2 exchanges them. In that case, Z2 is spontaneously broken. And one way, and this is one of the most central problems in theoretical physics, is to understand whether the low energy phase, the nature of the low energy phase. And one big conjecture by Landau in the last century is that we should be able to characterize most of the phase transition in terms of how the symmetry is represented in the low energy vacuum phase. So to understand how the symmetry, whether the symmetry is spontaneously broken or not, is one of the central questions in theoretical physics. And the order parameter is an operator such that if it acquires a VEF, it signals the fact that the symmetry is spontaneously broken. And that's what this operator sigma is doing. When you go to a symmetry breaking phase, this operator acquires a vacuum expectation value. And that non-zero vacuum expectation value tells you that the Z2 global symmetry is spontaneously broken. Disorder, on the other hand, is a very different object. It's not a local operator. It's something connected to a string. If you remember the lecture from yesterday, it will be something that connected to a product of the z's, the Pauli z's. It doesn't, it's an operator that does the opposite of the order parameter. Order parameter acquires a VEF when you are in the symmetry breaking phase. This order parameter acquires a VEF, vacuum expectation value, when you are in the symmetry preserving case. And Quermes-Wenier duality exchanges the symmetry breaking phase with the symmetry preserving phase. And therefore, it exchanges the order parameter with the disorder parameter. Yeah. It's a huge subject. I mean, it started with like Categorical, introducing disorder operator, etc. So it's really hard to cover everything in just a limited amount of time.
It's particular to this model, and it's not that any defect field like mu in another theory would be called disorder operator.
Everything is in the same model on this blackboard. Everything happens at the Ising CFD. These are just two different operators you can consider. One is a local operator, the other is not. But they are exchanged under this non-invertible symmetry.
I have a question regarding how D acts on sigma as it crosses, or when you consider like, sigma being surrounded by D?
Yeah, that's an excellent question. Yeah.
So I guess one manipulation that you can do is like bring D and make it like
yeah.
And then there is you have the fusion, and it appears there is eta, but there is also an identity.
Yes.
So this is what is confusing me.
Oh, okay. Yeah, let's do that. So you want to see explicitly how it works as I bring it through, right? So as you bring this line through, let's see, how do I draw? Yeah, I haven't done much. Yeah. And then you would have this.
Yes.
This vanishes.
E surrounding sigma vanishes?
That's right.
And then why it doesn't vanish in the when eta is?
Because it's attached to the eta line.
That's confusing.
Well, because I didn't explain it. This vanishes because you can do two of them. And if you do two of them, you can use the fusion rule. That becomes 1 plus eta. 1 plus eta is a projection operator. Z2, the sigma is Z2 odd. So it has to vanish. So D has to have a 0 eigenvalue. But that doesn't work for this one. And that gives you the disorder operator.
Thanks.
I didn't explain it because I wasn't intending to talk about this. So I shouldn't be apologetic about it. Any other questions? Great. All right, so in the remaining maybe 5 minutes, let me talk about 2 more examples. The first is the U1 Maxwell theory. We can pick a Zn subgroup of the U1 electric one-point symmetry. Engage the Zn electric one-point symmetry corresponds to rescale your gauge field by a factor. So that doesn't leave the theory invariant, right? It takes 1 over e squared to 1 over e squared times n. However, we define tau as 4 pi I over e squared. In Maxwell theory, there's a famous E and M duality. It means that the electron and the monopoles are on the same footing. In free Maxwell theory, that means the theory labeled by tau is the same as the theory labeled by -1 over tau. Now you see a glimpse of hope. Generally, when you gauge the Zn one-point symmetry, it changes the radius, changes the value of e squared, so you don't get back to itself. You don't get a big if. But now you can start with a particular value of tau. So the Maxwell theory has this continuous parameter e. In the real world, that's known as the fine structure constant. 1 over e squared over 4 pi is something like 1 over 137. If you take tau to be this particular value, so that corresponds to some particular value of the electric coupling, then if you first gauge the Zn one-point symmetry, this becomes tau over n squared. Wait, did I miss a square? I'm sorry, I missed a square. Each a is rescaled by a factor of n. Here you have 2 a's, so you rescale by a n squared. So you go from tau to tau over n squared. Well, and then you apply S duality, the E and M duality. So that gives you minus n squared over tau. This step is from here. But now you plug in the value of your tau. Let's go back to IN again. So, what did we learn? We learned that the Maxwell theory that tau equals IN is isomorphic to the Maxwell theory that tau equals to IN gauged by the Zn electric one-point symmetry. And that's the big if condition we would like to have. In this case, you have the non-invertible symmetry. And it satisfies the following algebra. E times d bar is C. And C in this case is 1 over n. Take the sum over 2 surfaces. And let's say B is supported in a 3 manifold n. What's my eta? I forgot to give my definition of eta. So this is just a general algebra we derived earlier. In this particular case, it means that d times d bar is the condensation defect, which is made out of the surfaces. All right. So maybe just one last example, which I hope only take me 1 minute. It's the 3 plus 1d, n equals to 4, super Young-Mills theory. That's U2 base. We have studied super Young-Mills, so let me just mention it real quick. So the n equals to 4 super Young-Mills has a Z2 one-point center symmetry. So you can start with SU2, and you gauge the center Z2 one-point symmetry, and then you get an SO3, n equals to 4 super Young-Mills theory, which is different from the SU2. However, there's another duality known as the S duality, relating the SO3 theory to SU2, while also exchanging tau to -1 over tau. Tau is a parameter of the super Young-Mills theory. And therefore, at tau equals to I, we realize that the SU2 Young-Mills theory is isomorphic to SU2 mod Z2. Okay. So these are the 3 examples I want to mention. The first is in 1 plus 1D Ising conformal field theory. Using the Cramer's linear duality, you find the non-invertible symmetry D. The second one is the 3 plus 1D free U1 Maxwell theory, the same theory that Maxwell studied. It has a non-invertible symmetry when the electric coupling is quantized in a particular way. By the way, this is also generalized to include the theta angle, and you actually find a very rich spectrum of non-invertible symmetry in the parameter space of free Maxwell theory. And the third example is the interacting 3 plus 1D n equals to 4 super Young-Mills. This is the maximally supersymmetric Young-Mills theory. It also has a parameter tau. Tau is I, it has a all right. So that's it about half gauging. And in my lecture, my final lecture in the afternoon, I'll talk about the QED example, which gives an alternative explanation for why pions decay in the real world. That's it. Thank you. Any questions before we go to break?
Yeah, can I do this in 1 plus 1D with compact boson?
Yes.
Just about the same.
Yes. In fact, in our paper, I think we did 4 examples. Any other question?
Is there any material feature of the dynamics of Maxwell theory that you can find at the special values of the coupling from or infer from the existence of the non-invertible?
I don't know. Yeah, that's an interesting question. I think no one knows. I mean, most of it is broken when you introduce electrons, etc. Right? Yeah, I don't know. I mean, we thought about it a little bit. Like, is it possible to detect the theta angle of the real world by studying the symmetries? But didn't get anywhere. I mean, this tells you something funny about strong CP, but we can discuss that later on. Okay, no more questions? Then let's go to the break. I think this one is also very difficult to give. The title of the talk is Why Do Ions of you must have heard the talk maybe 3 times, even 4 times. And the other half of the audience probably are not familiar with what pion is. It's a really mixed audience. I don't have a solution, so I'm just going to proceed. I'm sorry.
And the decay. Explain the pions and the decay.
It's already pion is the lightest particle in the real world made out of quarks. That's the end of my explanation.
And now decay.
So the starting point, unfortunately, requires some quantum field theory. Is something that you definitely would have learned if you have taken any quantum field theory class. It's in chapter 5 of Pascal and Schroeder. And
okay, I'm just going to read it.
And it's the 3+1D quantum electrodynamics. Right. So I'll be working with the signature. And the Lagrangian has the Maxwell term. I flip the sign because now I'm in Euclidean signature. It doesn't really matter. So this is just the free Maxwell so far. We talked about it in the last lecture. So now we want to couple it to matter fields. The thing we would like to couple to is the Dirac fermion. This is a 4-component complex fermion, the Dirac fermion. Okay. This is a U1 gauge field. And the Dirac fermion has unit charge, unit gauge charge. Now, classical event use the matrix. Now, classically, the Lagrangian has a chiral symmetry. Which rotates psi 5. Use one from 1, 2, 3, 4. Alpha red couples from 0 to 3. And alpha is 2 pi, e to the I pi gamma 5 is just a minus sign. And that's part of the U1 gauge group, and therefore the factor of 2. The factor of 2 doesn't really matter. Okay. But classically, this is a symmetry that lives it invariant. I mean, if you have never studied QED before, I mean, it takes some time to explain gamma mu, what the Dirac fermion is, etc. But you can take my words for it, that it's an elementary exercise that if you plug this transformation into here, it leaves it invariant. But quantum mechanically, that's not the case. Quantum mechanically, in 1969, Adler, Bell, and Jakiev show that U1A, A stands for axial or chiral, suffers from an anomaly. Now the word anomaly is heavily abused in physics, so let me say a little bit about what I meant by anomaly here. Anomaly, a 2-Hoof anomaly of a global symmetry means an obstruction to gauging it. But that's not what we are talking about here. Here, the anomaly, which is sometimes refers to as the ABJ anomaly, just means that U1A is not a symmetry quantum-mechanically. So this is the phenomenon where classically you have a symmetry of the Lagrangian, but quantum-mechanically the symmetry is not there. That was a famous result, in particular because you can apply it, and they did, to strong interaction. Of course, in 1969 there was no QCD, but I'm just going to present it in the language of QCD. You can apply this to QCD, and there's a similar anomaly for the pion physics. So as I said, pions are the lightest particles made out of quarks, up and down quarks. And there was a puzzle at that time. So pion comes with three families, pi plus, pi minus, and pi 0. The superscript denotes the electromagnetic charge of the particles. Now, there was a puzzle in the 60s where experimentally we saw that the neutral pions dominantly decays into 2 photons. But this large decay rate is incompatible with the symmetry structure known at that time. There was a U1A symmetry in QCD below the electroweak scale. And if this had really been a true global symmetry quantum mechanically, then there cannot be such a large decay rate from the neutral pion to 2 photons. But it turns out that that was what's experimentally observed. And that's where Adler, Bell, and Jakiv came to rescue. They said that U1A is actually not a true global symmetry quantum mechanically. The cross on it. And related to that fact, you actually have an effective coupling. F pi is some physical constant of mass dimension. You have an effective coupling between pi 0, you should think about it as a scalar field. Here F is the electromagnetic U1 gauge field. This term you can see that pi 0 is coupled to 2 photon fields, and that explains the dominant decay rate. So that was a beautiful story back in 1969. Led to many developments, and in many ways, the anomaly in physics came from their paper. Maybe one can argue that Schringer had it earlier, but in 4 dimensions it came from this paper. There's one thing that's slightly counterintuitive of the famous Adler-Bell-Jakiv result. I mean, not everything is correct, but just something slightly counterintuitive. So usually you would celebrate if you find a new global symmetry. I think that's what this Simon's collaboration is about. But in the case of ABJ, it's the opposite. They say that some naive symmetry you would have expected in your Lagrangian is actually not there quantum mechanically. So how come you can derive all these nice results that match with the experiment from the absence of the symmetry? So part of the motivation for the rest of the lecture is to provide an alternative interpretation for the result of Adler, Bell, and Jakiv. So instead of saying that there isn't such a symmetry U1, chiral symmetry U1A, actually there's a generalized global symmetry. And the generalized global symmetry also gives you the precise coupling between the neutral pion two. That's one motivation. Another motivation, which I really encourage you to ask your favorite physicist friend, is that is the chiral U1A symmetry a symmetry or not? QED. And I guarantee you that you will get a wide spectrum of different answers. This is a yes or no question. And really the answer you will hear most often is yes and no. That's arguably the worst answer you can expect from a yes or no question. But both are correct. And let me say a little bit why both are correct. No, because as we will soon discuss, there's no conserved current. if you remember from the previous lectures, a U1 global symmetry is defined such that if I have a J mu, a local current, that satisfies the conservation equation. But in the case of chiral U1A, there isn't such a thing. So from that point of view, you don't have a signal. On the other hand, it's also yes. And the reason is yes, which you can really, I'm not making this up. You can really see a lot of the classic papers that said yes and no at the same time. And the reason that it's yes is because there's no, the symmetry is violated by instanton. But if you work in flat space-time, which our world looks pretty close to, there's no abelian. By abelian, I mean U1, gauge group over there. There's no abelian instanton in flat space-time. So the cause of the problem, the instanton is what potentially ruins the symmetry. But there's no finite instanton action in flat space-time, so you might as well don't care.
Sorry, question?
Yeah.
Well, is there now been an instanton in flat space?
Yes, there is.
So what's the difference there?
The difference is that it is characterized by pi 3 of the gauge group. And here I'm focusing on the QED story where the gauge group is U1. And you might be wondering, if it only applies to U1 gauge group, why does it say anything about QCD? The reason is because by QCD, I actually mean QCD below the electroweak scale symmetry breaking. So the gauge group here is U1 ENF. So the non-abelian SU2 is already broken down to abelian.
So you have to use like a Higgs mechanism. You're using a Higgs mechanism to.
Yes.
Okay.
So well, there are two stories. You can look at the QED story on its own, don't care where it comes from, or you can think about QCD below the electroweak scale, where after the Higgs mechanism, you have the U1 ENF. And thanks for the question. And precisely because of that, we have nothing smart to say for the SU3 gauge symmetry. There's also an anomaly there, and it's not resurrected as any kind of generalized global symmetry. So it's only about the pion, but not about the eta prime.
I'm wondering, do you actually mean the conformal compactification of the flat space-time?
Yes. Yes. Okay. So another motivation for this for the rest of the lecture is to get a straight answer to this question. And I would say that the straight answer is that yes, there is a non-invertible global symmetry. But let me just emphasize again, nothing was wrong with the original interpretation. It is both yes and no, but we're just giving an alternative interpretation that fits into this modern language of generalized global symmetry. All right.
So is that right that a conserved current is sort of the translation of an invertible symmetry? Is that
translation of
it's translation? I mean the manifestation of it being an invertible symmetry.
That's right.
That's the point we're supposed to take.
That's right. So the point of view I'm taking is that the most general Lagrangian invariant way to define an invertible U1 global symmetry is the existence of a J mu that obeys this conservation equation, which we don't have in the case of QED. Okay. So in the case of QED, I'll mostly talk about QED, and it's very straightforward to apply it to QCD below the electroweak scale. In the case of QED, you can consider a current. Here, the superscript A is just to say that it's axial, it's chiral. So the current you would like to consider is this one. Famously, ABJ found that it's not conserved, but it equals 1 over 8 pi squared f wedge f. And here I normalize my gauge field to be such that my M2 manifold is 2 pi. So it is precisely the term on the right-hand side that bothers us. It's non-zero, so you don't have an ordinary invertible U1 global symmetry. Well, but let's see what we can do. So we will take this as the starting point, which Adler and Bell and Jacquet did a perturbative Feynman diagram calculation to find this relation. And then I think Bardeen showed that this is one loop exact, you don't have any further correction. So we take this as given and see if we can find a conserved quantity. And by a conserved, if we did find a conserved quantity, we might as well call it the symmetry. So the first thing you might try, which is what we did for an ordinary invertible U1 global symmetry, is just to take the currents and integrate it on some free manifold. The first thing you do is you take U alpha, take some free manifold M, it's codimension 1 in 4 dimensions. If there had not been the term on the right-hand side, the integrand is closed and therefore its topological is conserved. Now because there is a right-hand side, this quantity is not conserved, I'm going to use the word conserved and topological interchangeably. But for whatever that's worth, it's gauge invariant. Okay. So we fail. Now the second thing you can try, which Adler did try in 1969, is to observe that f wedge f is almost like an exact, well, it is an exterior derivative of the Chern-Simons form. So what he did is to define a different operator. I put a hat to distinguish from it from the previous one. If you take the exterior derivative of the quantity inside the parenthesis, you formally get 0. You get this equation. I'm moving this term to the left-hand side. So this thing is formally closed. So it's formally conserved, or topological. But the issue is that the red piece of the integral is not gauge invariant. Remember that A, as a one-point gauge field, has a gauge transformation. A goes to A plus D alpha. Alpha, oh, I shouldn't use alpha. Lambda is some zero form, some scalar field. And this is obviously not invariant. You might hope that after you do the integral, it might be gauge invariant. Well, if you do the integral, there will be a global term, and that's only invariant when this coefficient is properly quantized. In fact, you can see this is the Chern-Simons term, and the Chern-Simons term is only well defined in gauge invariant if the coefficient is quantized in a specific way. In that case, even though the integrand is not invariant, The integral is also not quite invariant. It's shifted by some 2 pi times the integer. But then the exponentiation of the integral is invariant. Let me just quote the fact, which you are not supposed to question me. The Chern-Simons action on the 3-manifold, to be more precise, a spin 3-manifold, is gauge invariant if and only if the coefficient n there is an integer. Which unfortunately we don't have. Because for us, the coefficient is alpha over a pi squared. But this is not the gauge invariant expression. And for the rest of the talk, I will put whatever that's not gauge invariant in position. And that was kind of the status back in 1969. You either have some gauge invariant garbage that's not conserved, or you have something that's formally conserved but it's not gauge invariant. The question is, can you have something that's gauge invariant and conserved at the same time? If you did find such a thing, then it should be called symmetry. The new development is the following. This is trial number 3. So to make progress, let's first be less ambitious. Let's take our alpha, the rotation angle, to be 2 pi over. And for simplicity, let me take it to be non-negative integers. The sign doesn't matter. You can also take it to be negative. And let's take a look at that operator. U hat 2 pi over n, 3, potential I, well, I over n star j minus my red chalk I here 4 pi n. Oh, we haven't done much. We just substitute some particular value of alpha into this expression. Now, based on the fact I quoted there, you see that this is still not gauge invariant because the integer, unfortunately, is in the denominator. Now, by the way, if you had began with a Dirac fermion with higher gauge charge, or if you begin with multiple species of Dirac fermion, change the coefficient here to some integer, maybe 7, and then there will be a 7 here, and that means that you actually have some leftover discrete symmetry. But I'm doing the minimal case. Try to, do the minimal case where naively the entire U1 symmetry is gone. All right. Now, any question at this point?
But if M3 is S3, the coefficient is arbitrary, right?
Right, okay, so the statement is that we want to define an operator on a general
non-trivial manifolds. Okay.
So what you ask is exactly what Adler said in 1969.
Yeah.
Adler said, our real world look pretty flat. So I might as well take M3 to be R3, or if you are more rigorous, take it to be S3. And then it's actually gauge invariant. So what Adler said is that there is a conserved engagement invariant operator in R3, in flat spacetime. And he's perfectly correct.
Thank you.
But the way we think about global symmetry these days is that we want to use it as some invariant ID number for our quantum field theory. And it's typically the case that someone will give us two different descriptions of the quantum system. Maybe one from the lattice, the other from a string theory. And you want to see if they are identical deep in the IR. And one powerful use of global symmetry is that it should be used as an ID number for us to identify or distinguish different representations of a quantum field theory. And to achieve that, it's important to be able to put your quantum system on general space-time manifolds. If you only put it on restricted space-time manifolds, it could be that two distinct quantum systems actually behave in the same way. And they're only distinguished by putting it on some more general space-time manifold. So from that philosophical point of view, we would like to define the symmetry more generally. We don't want to say this symmetry only exists in flat space, but not on more general manifold. It is a correct statement, but we want to have something better. And that's correlated with the yes and no answer that you typically hear. There's a second more practical way to address the question. You can say, if you talk to a particle phenomenologist, he or she would just say, our real world really look pretty flat, so why bother? Why do we care about all this topology? I never want to deal with topology in my life. That's a fair standpoint, but it's only fair if you don't care about monopoles. The moment you talk about monopoles, the existence of a very heavy monopole sitting there in the middle of nowhere will create an non-trivial topology, effectively.
You mean Callan-Rubakov effect,
Exactly.
right?
So for instance, Callan-Rubakov is the effect of studying a fermion scatter of a monopole. And that has actual consequences in Guts models and in proton decay, etc. This is the Callan and Rubakov are phenomenologists. And so in those contexts, when you do care about monopole physics, topology does matter. And that's another reason why you should care about whether the chiral symmetry is a symmetry or not. And it does have physical effects, because one consequence of the chiral symmetry in QED is helicity conservation. So as we were, a photon or a fermion can carry two possible helicities. If you scatter positron with electron, as people really did in an accelerator, you can check whether the helicity is conserved before the scattering and after the scattering. Take QED in the massless limit. Helicity is conserved. But where does this conservation law come from? This is some true conservation law you see in the accelerator. If you open any quantum field theory textbook, no one dares to explain the helicity conservation in terms of the chiral symmetry. The way they prove it, and I encourage you to look it up in chapter 5 of Paskin and Schroeder, is that they literally compute the Feynman diagram. They move the gamma 5 matrix from one end of the trace to the other end and show something vanishes. But they didn't dare to say that it's a consequence of the U1 chiral symmetry, because they know down to later chapter, maybe chapter 19, they will talk about anomaly and say that U1A is actually not a symmetry at all. So they didn't want to use it. However, as we said, in flat space-time, without monopole, in R3 or S3, U1 asymmetry is a good symmetry. And you can think about helicity conservation as a consequence of it. And indeed, the moment you have monopoles, the most famous result of Callan and Rubakov is that the moment you have monopole, the S-wave scattering of the electron of the monopoles violates helicity conservation. So you see, so that gives you a, but that's kind of puzzling. So why does monopole break the chiral symmetry? And that's hopefully what we will clarify in the rest of the talk.
I guess if it's a good symmetry in flat space, then how does this relate to the pion decay to photons?
Sorry, what was the question? Yeah.
Isn't the decay of the pion of the pi zero prevented by this symmetry? So if it's good in flat space?
Oh, I think it's actually the other way around. If U1A had been an honest to God invertible symmetry, then there would not have been the decay channel from pi 0 to 2 gamma.
Yeah, so then I don't follow. If in flat space you can argue that it's a good symmetry,
right?
Then how come that in an experiment in flat space like an accelerator?
I see what you mean. Let me see. That's a good question. Let me see how to address it. The question is whether you should really think about pi 0 as a Goldstone boson. And if U1A had been a good invertible symmetry, then pi 0 would be an honest to God Goldstone boson in the massless quark limit. And then there cannot be a pi 0 FF term. Now, the reason, and what ABJ realized is that U1A is not really a good global symmetry. So a pi 0 FF term is actually necessary to reproduce the anomaly. I guess I was too strong in saying that it has no effect in flat spacetime. It does have effect in matching the term over there. But it has no effect, say, if you just consider the scattering between electron and positron. I think that's a better way of saying it. In fact, the whole point of the talk is to get a better interpretation of this statement. This statement is not quite precise, and it has the fallacy. You just pointed out. All right. Any yeah.
You mentioned when you first wrote point 3 that the issue is that alpha has the n in the denominator.
Right.
I wonder if this U1 that you started with, I mean, there's a map from U1 to U1, which is just the nth power map.
Right.
If somehow that thing should act, the nth power map, and then the sort of fiber between those is a Z1n. That would be give a one-form symmetry.
It's related. It's related to the construction we are going to do. But let me just say that it doesn't work exactly the way we want. The reason is because in the free Maxwell theory, you have an electric one-form symmetry and you have a magnetic one-form symmetry. Gauging either one of them will rescale the U1 by a factor of n. Now, here we couple it to the Dirac fermion. So you actually lose one of the one-form symmetry. Now you still have another one. And you are asking me whether we can just gauge the other one, the magnetic one, to fix that issue. And that's basically what I'm going to do. So I'm going to first present it in a slightly different language, and then I'll try to connect back to the half-gauging picture we talked about last time. Any other questions?
If I would only gauge if I would only integrate over the fermions or only integrate over the gauge fields, would the U1 asymmetry be there?
Oh, if you have only integrated, if you're only integrating over the fermion fields, but not the gauge field, so you treat the gauge field as some background, then U1A would have been. Yeah, U1A is a good symmetry of the theory of the free Dirac fermion. Okay. And you see the analogy between what we talk about in the Ising model. In the Ising model, in the Ising model discussion, you can think about the free Majorana fermion. The free Majorana fermion has an invertible symmetry. That's the counterpart of U1A of the free Dirac fermion in 4 dimensions. Now, in the 1+1D, you start with the Majorana fermions, you couple it to a Z2 gauge field to turn it into the Ising model. That procedure is the analog of gauging the U1 symmetry of a Dirac fermion to get to QED with dynamical gauge field. And then the last piece of the puzzle is that yesterday we talked about how the invertible symmetry of the Majorana fermions becomes the non-invertible symmetry of the Ising model, in which case you view the Ising model as a Z2 gauge theory of Majorana. The analog of that statement here is that the invertible symmetry U1A of a free Dirac fermion will turn into a non-invertible symmetry of QED with dynamical gauge field. Any other question? So here we're still stuck. Unfortunately, this action appears somewhere else. This action appears in the discussion of a different community of physicists. That's the context of 2 plus 1D fractional quantum. I'm not going to say too much about the details of what a fractional quantum Hall state is. This is a topic our condensed matter physicist friends like a lot. What they do is that they have a tabletop experiment. So the space is a two-dimensional space, and you have a time direction. And you apply a large magnetic field to your material. You try to measure the Hall conductance, and you find some fractional quantization. There, this red action is used as an effective action to describe the fractional quantum Hall state. Where A, you should think about it as a background gauge field. That's very different from the discussion up there. That's why I drew a line. Below the line, A is a background gauge field for the magnetic field in your lab. And the space-time is three-dimensional. Up there, M is the locus where we try to define this operator. Down here, M is the space-time of your experimental physicist friends. But you could have asked, how could our condensed matter physicist friend who do real experiment, measure real physics, be working with a gauge non-invariant effective action? Well, there's a famous solution or explanation in that context. There's a more precise and gauge invariant effective action for the fractional quantum Hall state. And that's given by the following. In the blue action, we have a new dynamical gauge field, little a. It's also a one-point gauge field. In the blue action, you see that both coefficients of the Chern-Simons terms are properly quantized. They obey this rule. Well, here I didn't tell you what the rules are when you have two kinds of gauge field, but you can take my words that this is gauge. Little a is sometimes known as the statistical gauge field. Should put this in quotation marks because it's not gauge invariant. The little a here is dynamical, capital A here is background. We're integrating over little a, but not capital A. You can roughly think about the relation between the two by integrating out little a, and you get a relation that's something like little a equals capital A divided by n. But this is not precise because you cannot divide a properly quantized gauge field by a factor of n. And that's what you expect, indeed. You cannot perform legal manipulation to go from a gauge invariant action to a gauge non-invariant. Think about this as a more heuristic way to deal with fractional quantum Hall state. It captures correctly 99% of the physics, but if you want to work with a truly gauge invariant action, this is the one. So that's the story in fractional quantum Hall. Now, motivated by the fractional quantum Hall discussion, in trial number 3, we can try the following. We simply take our U hat over there and define a new operator. So we're still in number 3. And we define the new operator D. add to it this term. So we replace the problematic red term by the blue term. So now we have introduced a new dynamical gauge field little a. It's only integrated on the three manifold where we define this operator. So this little a doesn't contribute to any new asymptotic state in QED. Away from the operator or defect, you still have the good old-fashioned QED. Your states are positron, electrons, and photon, and that's it. Now this operator is conserved. This I will justify in a moment. It's obvious it's gauge invariant because the previous problematic term is now taken care of. The reason that it's conserved is more subtle, and that's related to David's question. So let me briefly comment on that. To rigorously show that it's conserved, we have to use the half gauging construction. You see that I constructed this operator without saying anything about the higher form symmetry. So it seems to be disconnected from the previous lecture, but it's actually not. This symmetry can be constructed from half gauging. And the hero of the story is the Zn one-form symmetry subgroup of the magnetic one-form symmetry. So as David asked earlier, the electric one-form symmetry is broken by the presence of the dynamical Dirac fermions, but the magnetic one is still there. And you can pick a Zn subgroup and perform half gauging. Now, if you remember from the previous lecture, that for the half gauging to give you a non-invertible defect, there's a big if that has to be satisfied. And in all the examples I provided in the last lecture, the big if is achieved by certain duality. Now, what is the duality in QED? We've never heard of any duality in QED. Well, the duality is roughly the following. It's because, let me first say the following. So when you gauge the one-form symmetry in a particular way, which I'm not going to spell out. You can see at my TASI lectures or the original papers to see how exactly we gauge the symmetry. But there is a way to gauge the Zn magnetic one-form symmetry such that the net effect is to shift the theta angle by 2 pi over n. Okay, some of you might not know what the theta angle is, so let me quickly say that. So in QED Lagrangian, you can add to it an additional term of the form f wedge f. F wedge f is locally a total derivative, but the theta angle term is still non-trivial. In massless QED, you will never see people write down an f wedge f term. That is because by doing a field redefinition, sine theta is shifted to theta plus alpha. This is a famous result by Fujikawa in the 70s, where he showed that when you do a field redefinition on the fermions in massless QED, that effectively generates a theta angle. And this is what we use for the big if condition. We first gauge this magnetic Zn one-form symmetry. We don't directly land on the original QED, rather the theta angle is shifted by a certain amount. But then in the second step, we perform a field redefinition, which gives me an isomorphism between the shifted theta angle and the original one. So at the end of the day, we do have the statement that QED is isomorphic to AD, modeled by a ZM magnetic one-force region. And now that everything is in place, we can apply the half-gauging argument using the topological boundary condition to argue that this operator is topological. Now it's completely not obvious why, if you follow these steps, you get a SEM operator. There's a non-trivial calculation to be done, and you can see my TASI lectures. Well, actually, I didn't talk about it in my TASI lecture. You can see the original paper, which is cited in the TASI lecture, to see that calculation. Okay, so where are we now? We start with an anomalous conservation equation here. We have trial number 1, trial number 2, both fail. But then we have, in the third trial, we did get a conserved n-gauge invariant operator. And that derivation, that operator can also be reproduced on half-gauge. Now, there's a price we pay. We pay is that this operator, while it is conserved, it's not an ordinary unitary solution. How do you check if something is unitary or not? Well, you take 1/n as an operator. So I'm not doing some fancy topological fusion. I'm really viewing D as an operator, where M is my whole space at a given time. So if you want, you can think about it as a Euclidean configuration where there's some defect, entire space at a given time. The more down-to-earth person would say that I just have two operators, and I add one first and I add the other next, and I see what I get. So how do you check if an operator is unitary or not? Well, you take that operator and you multiply it by its dagger. If you do that calculation, this term immediately cancels, because when you take the dagger, it flips the sign of this term. But importantly, you have a little a for each such operator. Here we have two such operators, so I should write the passenger row twice. There are two of them, I'll call them A and A bar. They're both real 1.8. And then you get a complicated expression. Now the details don't matter. The first thing you should notice is that it doesn't look like the identity operator. You can show this more rigorously, but let me not say too much about it. So you immediately show that D, while being conserved, is actually not a unitary operator. In fact, with a little bit more work, you can show that it's non-invertible. The reason that it's non-invertible is because you attach the fractional quantum Hall state to it. Fractional quantum Hall state is a non-invertible PQFT. So if you take my words that this is not the identity, you should ask, what is it then? Well, in the previous lecture, we keep saying that D times D dagger should be C. And indeed, this is a condensation defect. How do you think about it as a condensation defect? There's this little a bar in the way that looks extremely complicated. But don't worry about the details. The only thing you need to know is that it's some operator involving D capital A. Now, by this point, you might have already forgotten what capital A is, and it's no longer on the blackboard. Capital A is the dynamical gauge field for your U1 QED. Okay? It's the gauge field that gives you the photon. That's the reason we can see each other at this very moment. What is D capital A? That's the magnetic field. So what is this guy trying to do? Oh, sorry, I'm missing this one. This is an operator. So I'm writing the whole right-hand side as C of M3. This operator is supported on a 3 manifold, and it's a function of the magnetic field. But when you learn undergraduate electromagnetism, the magnetic field is defined on a 2 surface, Right? You literally draw a two-sphere and you measure the magnetic flux. That's the magnetic version of the Gauss law. You have never heard of a magnetic flux through a three manifolds. That's where condensation effect comes into play. So recall, what is a condensation effect? In 2 plus 1D, in one dimension lower, I want to go to one dimension lower because that's the dimension I can draw pictures. The condensation surface defect is actually a mesh of lines. So it's a way of inputting some lower dimensional defect to get a higher dimensional one. And that's exactly what's happening here. You have a magnetic surface. You start with some magnetic surface. We've got two surfaces in four space-time dimensions. You do some manipulation to create a three-dimensional operator. So this is exactly a condensation defect of the magnetic one force. One quick comment is that it's actually easy to generalize this construction to any rational number. So previously we did 1 over n, now you can do any rational number. E over n is q mod z. So at the end of the day, what we found is that the invertible U1 chiral symmetry, this is a history timeline of the fate of the U1 chiral symmetry. Before 1969, everyone thought chiral symmetry is there. After 69, everyone thought chiral symmetry is gone. The new development in 2022 is that chiral symmetry is actually non-invertible and labeled by Q mod Z. And at the level of the slogan, you can say that the fractional quantum Hall state cures the ABJ anomaly. And if you look back in history, it's actually kind of funny. There's no way that Adler and Bell and Jacquet back in '69 would have thought about curing their anomaly by a fractional quantum Hall state. The reason is because fractional quantum Hall state is only discovered in 1982. But this is a nice synthesis of the two topics. How much time do I have left? I started a little bit.
Like 5 minutes?
5 minutes, okay.
Something like that.
All right. So let me just wrap up with what? So I'm not going to say too much about QCD, I'm just saying in words. There's an identical construction in QCD, and by using this generalized, this non-invertible global symmetry, you can reproduce the pion decay rate. So that serves as alternative derivation for the ion decay. Now, in the remaining 5 minutes, I want to compare this story to the Ising model. So the Ising model, that's in 1 plus 1. That's where we started. In Ising model, there is a Z2 zero-point symmetry. That's an ordinary Z2 symmetry that flips the spins. Using that, you can say apparent Z2 symmetry. We get a Shao non-invertible symmetry D that obeys the algebra D times D is 1 plus eta. And you should think about 1 plus eta as the trivial version of the condensation defect. And the way that the D interacts with the local operator is that you can take this older operator, which is Z2 odd, bring it to the other side. And that will create a branch cut, which is the Z2 defect line on the other side. And that exchanges the order with this order. Now on this side of the blackboard, we're talking about 3 plus 1 DQED. in 3 plus 1D QED, there is an invertible symmetry. It's the magnetic one-form symmetry. In fact, we have a U1 magnetic one-form symmetry. But for each dP over n, we pick a Zn subgroup to do the half gauging and construct this non-invertible symmetry. So this is the parent, and the non-invertible symmetry is dP over n, and dP over n times d minus p over n, which is the same as the dagger. There's some condensation effect labeled by n. And how does the non-invertible symmetry act? And that's related to the Kalin-Rubakov effect. This non-invertible symmetry acts completely invertibly on the fermion operator. It acts on it just as a chiral rotation. So if you are a person who only cares about positron and electron, this is as good as an invertible U1 symmetry. And that's the statement why if you only do electron and positron scattering, it's as if you have an invertible U1 chiral symmetry. But things get interesting when you talk about monopole. So here I draw a circle to represent some Kahoot line. And you think about it as the monopole work. So this is 3-dimensional. This is 1-dimensional in space-time. It's a war line of a heavy monopole. Now, as we bring the monopole to the other side of the non-invertible symmetry, it experiences the gauging, just like what happens to the older operator. The older operator is Z20I. So as it goes to the other side, it's being gauged, and therefore it's attached to a Wilson line. The monopole is charged under the parent magnetic one-form symmetry. And therefore, as it goes to the other side, it's no longer a line operator. Just like a gauge non-invariant local operator should be attached to a line, a gauge non-invariant line operator should be attached to a surface. And this surface is nothing but, here is eta, here is also eta. Well, I will not write eta, but it's the integral of f the integral is over this 2-dimensional region. You can deform it such that it's just the interior of this disk. Okay, so what is this object? The white line is the monopole that carries a magnetic charge. The blue integral is almost like a total derivative. The integrand is almost like a total derivative. So you are extremely tempted to write it as a line integral along the white locus of A. But you cannot do that. The reason you cannot do that is because the coefficient has a 1 over n. So it's trying its very best to be an object carrying electric charge 1 over n. And that's a dion. So you get a dion where the electric and magnetic charge is 1 over n, comma 1. Whereas here, the monopole has electric and magnetic charge being 0, comma 1. So in the Ising model, the non-invertible symmetry is implemented the order-disorder transformation. That's the Kramers-Wenier duality. And here, the non-invertible symmetry in QED is implemented the Witten effect. Witten taught us as you shift the theta angle, which we did, here, a monopole becomes dion. All right, I'm running out of time, so I would just like to conclude that the Ising model is a very different quantum system than QED. But from the way I presented on the blackboard, I hope it's clear that there's actually some similarity between these very two distinct quantum systems. And that's really, in my opinion, the beauty of symmetry. It's really the generalized global symmetries that organize these two distinct quantum systems into a single formalism framework. All right, thank you.
So what are the fusion rules of this C?
Of C?
Yes.
Right. Did we work it out? I don't think we ever work it out in complete generality. I think we'll work out some special cases. And I think it's an interesting question to work it out completely. I have a project related to that and still ongoing.
So for the fusion rule of dp with d minus p,
yes.
Why do I have on the left-hand side p's and on the right-hand side I only have n's?
Oh, yeah, it's not a totally trivial fact. Am I able to explain it in real time? I kind of can. It's not a completely trivial fact because I didn't tell you what dp over n is. I just told you that it can be done.
dp over n is not the composition of d1 over n p times?
No, the algebra is more complicated than that. So if you have dp over n, d minus p over n, that means you are doing gauging in this the middle region. Now p labels some SPT phase or discrete torsion. I don't know which one would make more sense, or maybe diagonal width and twist if you wish in this middle region. Okay. Say the same thing in 3 different languages. Now you bring them very close to each other. The statement is that that particular diagonal width and twist becomes trivial when you put it at the interval with Dirichlet boundary condition. Well, trivial, yeah. Trivial in the sense that it's independent of P. And that's why, at the end of the day, when you fuse them, it becomes higher gauging, and the higher gauging is independent of that twist. It's not a trivial thing. It's something you have to check. There's a map from that diagonal width and turn to a diagonal width and turn in the lower dimensions. Yeah. This P corresponds to some H4 class. And the map is to some H3 class. And the statement is that for that particular choice of P, this map is independent of P.
It seems like when you move the monopole across this defect, the charge is not conserved.
Oh, that's an excellent question. That's an excellent question. So that's what we think. So first of all, what should be conserved? That's the question. What should be conserved? The global symmetry charge should be conserved. The gauge charge, as we said, is always a confusing way to talk about something. So here I make sure every global symmetry charge is conserved. So it's not a big issue that you get a fractional electric charge. However, in a related context, in a very closely related context, in the case of axion, this whole story has an intimate relation to axion. Or maybe half of you don't know what an axion is. It's a proposed light particle that's introduced to solve some phenomenological question. It's really closely related to axion because the neutral pion behaves like an axion. And in the context of axion, there has been it has been known for decades that electric charge is not conserved. And the idea is because the axion string superconducts. And the non-invertible symmetry actually gives an elegant way to tell you exactly how the electric charge fails to be conserved. Another way to say it here is that what really measures what you might call the gauge charge is the one-form symmetry. But in this model, the only one-form symmetry you have is the magnetic one-form symmetry. The electric one-form symmetry is gone because you have dynamical Dirac fermions. So electric charge can be screened. However, magnetic charge should be conserved, and indeed here it is conserved.
Is there, I don't know if this is well defined, but is there a way to relate the fact that non-invertible symmetries turn genuine operators into non-genuine ones, and the absence of a conserved current? Or are these just independent facts?
It's related. Let me see. Good question. Are they independent facts or not? I mean, all this construction are tied together, so it's hard for me to say. Okay, let me say the following. If you really have a conserved current, then you necessarily have an invertible symmetry. You have a current, you have a charge. You take the exponentiation of the charge, exponential is invertible, and therefore it's invertible. If you have an invertible symmetry, you are not going to be able to create such a thing, just because this is a junction. In that sense, but it is a general fact that the non-invertible symmetry map is given a local operator or one operator. I don't know if that's the answer.
The second is always confusing. When you get into the QoC, the construction is useful, is alright. And there is this other paper by now. Where it's like upgraded to a U1 again. Which to me, the reconstruction seems similar in some sense. Again, adding some field balance.
So, if you only know this part of the story, you might think, okay, so why can't I do something even more drastic? Something like what Inaki collaborates and Nabil did, and also like what Afner did. Now, the history is that when we wrote the paper, this is not our first derivation. We constructed the defect using half gauging because we feel most comfortable with half gauging. This only served as a heuristic derivation. And the reason we love half gauging is because half gauging, which I forgot to mention, half gauging manifestly gives you a defect or operator that satisfies the operator defect principle. If you just write down a conserved operator, you are not certain if you can do Vick rotation and turn it into a defect that's associated with a well-defined universe. Half gauging does that. The reason is because half gauging is constructed out of a topological boundary condition for a DFT. The topological boundary condition of a DFT necessarily gives you a well-defined space. So this construction guarantees that at the end of the day, this D can serve A as a conserved operator, B as a defect. It's not entirely clear to me whether other construction also satisfy that property. All right. So I will say that's one difference between the two constructions.
Okay, so it's a genuine operator, then it's even one operator, it's a set. It's not obviously if it's a defect or not.
That's that point. That's how I would put it.
So is it like sorry, but is it like really necessary?
That's an excellent question. So you can say, as I said, you can take any quantum field theory, put it in the compact space, take the space to be very small, so that you are just working with quantum mechanics. If you take that viewpoint, no problem. This is a conserved operator. It acts on the Hilbert space, and but then you just become a quantum mechanical person. But if you want to work with quantum field theory, I would advocate that there are more conditions to be satisfied. And in fact, I shouldn't say I, because these conditions are the exact same conditions that was advocated by Cardy when he classified boundary conditions in conformal field. So violating those conditions are just equally good or equally bad as violating Cardy's condition.
Wanted to say that I also struggle with this other U1 non-invertible, but I think that if there is some auxiliary path integral, and if you do it, then you find that for there is a formal U1 angle, but then for these rational values is the same, and for all the rest of the values, the path integral vanishes.
Yeah, exactly. Yeah, I remember something like that. Yeah, just that you said it now.
So I don't know how fair it is to say that it's a continuous U1.
Yeah, it's just like it's a Q over Z plus you add all the part that make it U1, but they don't do nothing. This is
it's like a zero.
Yeah, right.
Okay. The reason I'm tempted to say that only the Q mod Z parts are in a way more healthy is because there's no irrational quantum whole state. There are only fractional quantum whole states.
I have a question about the physics of this condensation process. So here's a physical experiment. If I throw a soccer ball at a soccer net, it stops the ball.
Right.
If I throw a golf ball at a soccer net, the golf ball goes through. So there's a mesh size to the net, and there's a certain difference between throwing something bigger than the mesh size and smaller than the mesh size. Mathematically, when we talk about this flooding of a defect, we're quite happy to imagine sort of, you know, a sort of infinitely dense sort of thing. But I wonder if in physics, if you actually keep track of, you know, if you do things with dimension, so you have Planck's constant and interaction length, if there's a sort of well-defined place where the condensation makes sense and where it doesn't.
I don't think the scale matters, because every manipulation here is topological. So the actual size doesn't matter, but the dimensionality absolutely matters, and for precisely the same metaphor you just said. And that's one important property of the condensation defect that we have in mind. So for instance, in 2+1D is the mesh of lines, and therefore it cannot possibly act on the local operators, because it's porous to the local operator. So it can act on the lines. But I have to clarify what I mean by act.
But I guess if you had a field that fell off at, you know, 1/r versus 1/r squared or something, if the drop off of a field were, is that what you mean by dimensionality, or?
Oh, sorry, by dimensionality I mean when there's a line defect or a point defect or a surface defect.
Yeah.
But there's no correlation, right? So the construction is, this is a topological symmetry if you wish. So there's no fall off correlation. Everything is topological. But I do agree with you. I mean, it doesn't act on the local operator, which is infinitesimally, which is a point.
Isn't this the same as the flooding of Tail-Johnson plate?
Okay, that's
I mean, this should be like a network that is built up of idempotence. So going back to his question, it shouldn't matter the dimensionality of his dimensionality. When he says that the size.
The size of.
Yeah, the size of the, you know, the displacement. This is what I'm saying of the defects, because at the end you could just replace that with just one line.
I can replace what by one
The
line?
network.
Well, I thought I still have to sum over all non-trivial cycles. Not
Yeah, but
just
at the
one.
end you can just, I mean, all that drawing. I
Yes.
think that he's saying the drawing of the network.
Yes.
The size, that
Yes.
size there.
Yes.
Not the size of the network.
But it has to be a network that contains all the the cycles.
Yeah, but I'm saying the same thing.
Okay. And then what? Sorry, I missed the.
So I think that he's saying that you can replace that. So he's
Replace the
worried.
network by-
He's worried. I think that you can have the distance in between the different lines. Okay.
Okay.
That matters.
So that shouldn't
it
matter.
doesn't. Yes,
Okay,
this is
it
what I'm
doesn't
saying.
matter. Okay,
Yes.
good.
So
Okay.
this is exactly the Tail-Johnson-Braid's argument.
We're certainly inspired by their paper, but I think it's above my pay grade to really say that our construction is the same as theirs.
So
I think it's certainly related, and when we wrote the paper, we were certainly inspired by their paper.
But you think it's not the same thing?
Well, as I said, it's above my pay grade to say it there. I'll see the fifth. Oh, yeah, sorry.
You mentioned this relation between order and zero.
Yes.
And is there an interpretation in QED which is similar? Like, is the monopole and is there an order parameter?
Right. I mean, you can think about monopole as the order parameter for the one-form symmetry, right?
Yeah.
Yeah, for this, whether or not the magnetic one-form symmetry is spontaneously broken. Yeah. So, yeah, so it's exactly the same. That Wilson lines and the group lines are the order parameter for one-form symmetries. Yeah, and you just bump up everything by 1 degree.
No, just two questions. One is just technical. So you say that to prove that that is conserved, you have to go to half gauging, but doesn't just follow by some sort of word identity for the blue theory? Or it seems to be right.
Yes. The short answer is yes, but the more precise way to say it is that this is a response theory in condensed matter literature, language. And the field theory way of saying is that you have a certain one-point symmetry anomaly. As long as you get the anomaly right, this is topological. Yeah. I don't think I'm disputing that argument. I just personally always find half gauging much more satisfactory. Because in all those arguments, there are some intermediate steps that you might have to do this manipulation. But there's a better way to say it. This manipulation is wrong globally. But topological or not is a local property. So to show the topological nature, you don't have to worry about such global issue, and you can just check whether the response is correct. And in that sense, this argument is also as good.
Just the other question
is,
so for like this problem of pion decay, the only important thing is to show that in some sense the current is conserved, right? Which is what you do.
Yeah.
But on the other hand, I mean, now you discover all this algebra. Does this tell you something more about the pion decay or general?
For pion decay, I don't know.
But
more generally, there are some new applications of similar non-invertible symmetry in axion physics. So it gives you some universal inequalities between various symmetry scales in the context of axion physics. And there's also another paper by Zohar and collaborators where they study the Kalin-Rubakov effect in this formalism. And the non-invertible symmetry, and as well as the higher group, resolve some of the puzzles in the literature in the context of model scattering.
Is there a physical question to ask whether there are proof anomalies for this?
Yeah, I think it's a great question. I don't think we analyzed this particular case. For the Maxwell theory case, which I talked about in the previous lecture, there are generally 2-Hoof anomalies for them. And here by 2-Hoof anomalies, I mean the incompatibility of that symmetry with the trivially gap base. And the answer is extremely interesting. It depends on the number theoretic property of n. In this case, I don't remember if we worked it out. Probably did. But there's a similar analysis you can do. Maybe someone else did. I lost track.
But is there like a stupid way of doing this by just computing the triangle diagram with the wrong non-invariant object?
I think intuitively I agree with that. That I feel like this non-invertible symmetry dp over n should be anomalous because it kind of inherits the anomaly of the U1 chiral symmetry of the free Dirac curve. But I personally didn't do the calculation, but it can be done. It's not difficult. It's very similar to the Maxwell calculation.
You cannot check for top anomalies like by gauging this
No, that's not how we compute the anomaly. So,
but because you don't know how to do it, or because it's just
because I don't know a comprehensive way to gauge such a non-invertible symmetry in 3+1 dimensions. I don't think people have fully developed that. Maybe people have, I don't know. So again, there's another, the related question is that how do we even define a 2-Hoof anomaly, right, for generalized global symmetry? Conventionally, 2-Hoof anomaly is defined as an obstruction to gauging. But to define the anomaly this way, you have to first define what gauging means. There's a, in a way, more universal definition, which is the definition taken by many practitioners of generalized global symmetry people this day, is to check whether the symmetry is compatible with a trivially gap base. And that definition does not require you to say what you mean by gauging. If you follow that second definition, there's an easy way to compute the anomaly.
So I have an unrelated question. So that's like somewhat when you have like just anomalous symmetry, you can construct an invertible different just stacking it with some but you're saying, yeah, this is a way. It could be like problematic also in the sense like of and the half gauging fixes this. In a sense, I can find the right gauging and check if this is okay. Is this always doable? Like if I give you some theory, some anomalous symmetries, I construct the an invertible defect just by studying it. It's on TQFTs, they're all classified more or less, so it's a global thing. Can I always find?
I don't know the general answer, but in most of the examples that I have studied in details, half gauging is reasonably effective. I'm not saying that it's exhaustive, but it's very general. And we talk about several examples, right? There's Ising, there's Maxwell, there's 4D equals to 4, there's QED, and there's Axiom. Right. So somehow half gauging always seems to work. I mean, there are other kinds of non-invertible symmetry, from disconnected gauge group. They're kind of qualitatively different, but half gauging certainly covers a lot of them. Thank you again.